Hello, good morning everyone, and welcome to our course, Computational Spectroscopy, Hands-on Many-Body Calculation with the Yambo Code. This course is organized in cooperation by Max Center of Excellence and EuroCC Czechia. And before we start, I would like to just briefly introduce you to our tutors who will guide you through the lectures and hands-on sessions. And it is Daniele Varsano, Giacomo Sesti, Andrea Ferretti from CNR Nano, Matteo De Alessio from University of Modena and Reggio Emilia, Claudia Cardoso, Nicola Spallanzani, Fulvio Paleari, also from CNR Nano, and our colleague from IT for Innovations, Lumomir Riha. So before I give the floor to our first speaker, I just would like to mention that this course is being recorded, but only its lectures and theories, no hands-on parts, and video will be available afterwards on our YouTube channel. So this is all from me. Thank you for attention and enjoy your course.
So I think we can start. So let me introduce myself. I'm Daniele Varzano from the Italian Research Council, Sierra Institute of Nanoscience. And yeah, I'm also among the developers of the Yambo Code, and I'm a member of the Max Center of Excellence. In particular, I do coordinate the train activities in the center. So it's a pleasure to give these introductory lectures, and I would like briefly to spend some few words about the Max Center of Excellence, and then I will provide you a very basic historical background and introduce some basic concepts of many-body perturbation theory, which is the topic of this school, and also an overview of the Yambo Code you will use in the second half of these 3 days. I don't know actually your background, so it's possible that for some of you these introductory concepts are too basic. I don't know. Anyway, I would like to put everything in the right context, and I hope you will appreciate. So the Max Center of Excellence actually started more than 10 years ago. And it is nowadays in the third phase. And the center, the project will expire at the end of this year. And during these 10 years, the activities of the center have, let's say, followed somehow the progress that you have assisted in the HPC architectures in Europe. So here, just in one sentence, I summarize the main topic of the activities declined in different action. But the first phase, I mean, we put the foundation of porting first principle codes on material science. That are the main object of the center in to large scale architectures, and we work a lot on the software interoperability. In the second phase, we target the pre-exascale machines. I mean, these are the years where in Europe appeared the first pre-exascale machines. So there was a lot of works in importing and benchmark, in particular on hybrid architecture, GPU. And in this third phase, now we have since a few months, let's say, the first exascale machine in Europe, and we are working to exploit our codes at full scale performance, also integrating with exascale workflow, with also a work done at FRI on energy efficiency, and you will hear about this in the following days. So why Max and why Center of Excellence in Europe, HPC in general? I mean, we have assisted in these 10 years through an abrupt change for what concerned the high performance computing. So we have exascale, exaflops. We have the possibility to access exaflop machine. This is a change that needed an action for full explosions. Here, this is Jupiter. I don't have the pointer, it seems, but okay, probably it's not needed. Jupiter that started his operation a few months ago, and here also the pre-exascale has Lumi and Leonardo that are in place since some already since some years. So Max, in particular, is devoted to quantum mechanics-based atomic modeling of materials. So essentially, are electronic structure methods, which are highly accurate, and also this comes with the high demanding of computational resource, and this provides an opportunity both for what concern not only the time to solution, but this allows also for higher accuracy on the method and on high throughput screening in the field of material science. Okay, for what concern the Yambo Code, in particular here, this allows us to treat larger and larger unit cells, structures, and the possibility of study with high accuracy, also complex experiment, as here just an example of angular resolved photoemission experiment. You will hear on this topic in the following lectures and also in this lecture. High accuracy, but also high throughput screening. This is an example of a high throughput calculations on metals. This is another one on 2D material, exfoliation on 2D materials. And these are the codes that are part of the Max Center of Excellence, and which are Quantum Espresso and Siesta, density functional theory codes, these are community codes with a very large basin of users. Then we have Yambo that you will hear in these 3 days about many body perturbation theory. There is also big DFT, that is a linear scaling DFT code. Fleur, again, a DFT and many body perturbation theory code, very accurate, in particular for magnetic system. And AIDA is a platform that's very useful to orchestrate calculation in high performance computing framework. This is the consortium, so at the base there are the codes. Then we have several university and research centers hosting the developers of the code. We have data centers, so the machines, the HPC machines that are part of the consortium, and also technology and co-design partner. And yeah, selected activities of the Max centers. So there is a lot of work done on the codes. Here in this pie, just to show that this is an approximate usage of HPC resources in Europe, separated by topic, and you can see that chemical science and materials are a big part of the usage of the machines. And in Max, we dedicate our work on optimization, performance portability, of course, GPU support, extra scale workflow, and also co-design, energy efficiency, and there is a large effort on the education and training through school as this one and hackathons. Before concluding this short presentation of the Max Centers, we have, we together with other institutions in Max, co-developed a training platform. This is Lumos, you can find on the web. And this is quite agile platform containing training materials you can explore. It's divided by channel. Each channel contains collections of lectures and schools and training material and curated video lecture you can easily navigate. This is just a snapshot of a past school done some years ago. Okay, this is, sorry, this alpha is not present anymore. The address is lumos.org, has been released officially. Okay, let's start with our journey now. Now I would like to provide some historical background on computational material science and how many-body perturbation theory insert in this story, which, as you will see, is not that old. I mean, what we are doing now is not started not so many years ago. Here, this is a chart starting from before the 17th century, where the way to do science was actually empirical. Here, these are named paradigms. I don't think it's a correct way epistemologically to call in that way, but just to highlight the back two we had in the history of science. So, sorry, I have the cat that is this. And then during the 17th century, we start, I mean, from the empirical side, basis of observation experimentation to the first scientific laws. And the computational science, actually, we will see in a moment, so this, when we started to use the computer to do simulations, is about 70, everything started about 60, 70 years ago. And nowadays, we are entering in the era of big data and artificial intelligence science. This will be not a topic of this school, but as you already know, nowadays I mean, this has pervaded all the domains of the science domains. I don't know if there is a date when computational material science starts, but probably is with the work of Bernie Julia Halder in the United States. It was awarded by the Boltzmann Medal, where he used this IBM 704 in Los Alamos. This was the laboratory for the Manhattan Project, so military applications, and he had access to these machines and had the idea to use the computer to prove some laws of statistical mechanics. And this is, I would say, the first simulation. It was an hard spheres model where it was studied the phase transition from liquid to solids. This is the beginning of this paper. The method consists of solving exactly the simultaneous classical equation of motion of several hundred particles. Just to have an idea, well, first of all, together with Alder, there was Marianne Mansig, I mean, what's actually who wrote the computer code, maybe the first scientific computer codes, and should be recognized. And just to have an idea, the machine that is here on the right in this big room, if we compare with our chip now, it's 9 orders of magnitude lower than a modern mobile phone. Okay, so was classical, anyway, classical mechanics was evolution of Newton equations. Uh, what about quantum mechanics? Well, I put here a bar on on 1933. This is Erwin Schrödinger, the Nobel Prize in Physics, with this paper of the 26 quantization as an eigenvalue problem. So the Schrödinger equation tell us how to calculate the grand state and eventually the evolution of a quantum system. Now, this is I wrote here, as you have seen in many books, the Hamiltonian of a system of interacting electrons. This is the eigenvalue equation, the equations, and this is the famous Dirac sentence. We know the laws. And we can treat the universe, if you want, the physics of the whole chemistry. And the difficulty is that the application of these laws leads to equation much too complicated to be solvable. So the idea is we cannot solve them, let's use the computer. Unfortunately, this is a many-body problem. This is the many electron Schrödinger equation, and the scale is exponential. So this is the so-called exponential wall, and here I did some very easy maths, assuming the solution of an eigenvalue problem, time to solutions, and see how this is scaled. For instance, if you want represents this wave function on 100 by 100 by 100 points on a real space grid, and you end up that treating a few centon of electrons, the solution of this equation with a modern computer will take a time that is larger on the age of the universe. And at the same time, if we want to store this wave function with the same number of electrons, few electrons is the global annual data storage. So it's not a merely technological issue. We cannot wait for more powerful machine to afford our many-body problem. Simply, we have to find a different way to treat the problem because we cannot compete with the exponential scaling, both in memory and in time. So here comes another Nobel Prize. He is Walter Kohn, 1964. And he came out in 64 with a theorem and in 65 with a scheme together with Liu Sham. And this is the density functional theory. Most of you, I think you are practitioner and you heard about that. So probably I will not enter too much in the detail of the DFT. Anyway, just to say it is based on a theorem that provide a one-to-one correspondence between the ground state of an electronic system and the external potential. And this one-to-one relation brings us from the 3n variable of the wave function to the 3 variables to determine all the ground state properties of the systems. Of course, this is a very nice theorem of quantum mechanics, but then it is formulated in terms of a functional that is universal, but this is also unknown. So the theorem itself does not provide a way to calculate anything. So a Nobel Prize for them, maybe yes, but not so. I mean, is it deserved or not? I think it is because Walter Kohn also came out with a practical scheme. The practical scheme has the Kohn-Sham equation of density functional theory. So there is here the idea that we can, from a full interacting system, we can switch to a non-interacting fictitious Kohn-Sham system that we know how to solve. This is very important because now we can use our computer and solve the equation of these auxiliary systems. And we know that if approximation are well controlled, we can have a good estimation of the real density of the interacting system. So the DFT replace the exponentially complex wave function to a system that now it's not more exponential, it is polynomial. And this allow us to treat systems, and nowadays up to 1,000 or tenth of 1,000 electrons can be solved with density functional theory. Of course, the price to pay is that we need to approximate all the complexity now in this exchange correlation functional. If we could know how it is formulated, it would be a miracle. We don't know it, but we know how to approximate it. And during the last, I would say, 30, 40 years, it has been a branch of research to find good approximation for the exchange correlation functional. This is on the left is one of the first functional that provide very good results, reasonable results, not for all the systems, the so-called local density approximation. So a very simple approximation that approximates the exchange correlation energy, density of energy, to the one of the uniform electron gas calculated in that point at the density of the uniform electron gas. And this start to to provide reasonable good results, to be protective, and I would say that the success of density functional theories mostly relies, and the interest on the theory relies in the successful of this simple approximation. Then here on the right, I put this picture taken from the paper of inspired from the famous paper of John Perdue, that is the so-called Jacob lectures from the Hartree world to the heaven of the chemical accuracy. And this is a hierarchy of exchange correlation functional. Now we use this hybrid meta GGA double hybrid that provide more and more accurate results. Just to mention that before I was showing this new paradigm of machine learning, and exactly in these days it was released a few months ago from Microsoft, a new exchange correlation functional based on modern deep machine learning. And I've not tried it, but I'm pretty sure that it will work very well. Okay. So, since its beginning, the density functional theory provide very good results. Here on the left is a plot of the density. This is a biological molecule. This is the adenine nucleobasis. And this is the plot of the density functional theory calculations that nowadays you can do in your laptop. and the density extracted from X-ray experiments. And as you can see, the agreement is impressive. As well, here in the center panel, this is density functional perturbation theory, phonon bands, phonon modes, calculation practically on top of the experiments. So here the predictive power is impressive. And here for what concern, for instance, lattice constant of bulk material, this is an accuracy test on ternary oxides, and we are talking of errors that are never larger of 3-4% with respect to the experiment. So density functional theory works very well. This is also testified here. These are the top 10 cited papers in all science. This is statistics done in 2014 on the left, 2025. In 2014, two papers of the top most cited papers in the literature were about density functional theory. 2025, there are three papers, so here to testify the relevance. And here on the right, the number of paper published containing the keyword density functional theory, and you can see this is an exercise I did on January, so a few months ago, and you can see the exponential growth of the activity on density functional theory, and on the bottom divided for topics. So not only material science and chemistry, but you can see that is also used in pharmacology, computer science, and energy, environmental science. So really pervasive. So we are very happy with the density functional theory. It is the most used technique, I would say, in electronic structure calculation nowadays. So why we don't stick with density functional theory? Why do we want to go beyond that? Well, let's see. Um, let's see how do we probe the property of our materials. There are several techniques. In here, as an example, then I will come out with other observables. Let's have a look at what happened in an absorption experiment or in a photoemission experiment. Photoemission experiment, what is called a charge excitation, because we add or remove an electron from our system, and this is exactly the way to probe the materials. So in direct photoemission, we shine our sample with light, unknown frequency. Photoelectron effect, electrons from the materials will be ejected. We measure the kinetic energy, and we can have an insight on the energy level of that electron that was in the material before the light excited. Absorption are named neutral excitation because electrons are not ejected, but just they acquire more energy inside the sample. So this is direct photoemission experiments. These are the equation of conservations of energy, so initials and final state. We can also consider the conservation of momentum to have an angle resolved resolution, and from here comes the measure of band structure. So essentially the density of occupied states of our system. For inverse photoemission, it's very similar. We add an electron on the system. The electron will occupy an allowed energy levels of the systems, and photon is emitted, is measured, and from the conservation of energy we can measure this quasi-particle level of unoccupied states. So as you can see in both experiment, because of this conservation of law, we have to consider energies of the system in its ground state n, and the energy of the system when an electron has been added or removed for the systems. This is a way, for instance, to measure the gap in a semiconductor. And so very important technologically to know the gap of materials for many applications, from transport to photovoltaic and so on. And the gap essentially is measured as the electron affinity minus the ionization potential. As you can see here, it involves the knowledge of the total energy of the system with an electron added or subtracted. And this process of ejection of an electron is indeed a many-body process, because it involves then relaxation of the system, and as we will see in the following lectures, the screening of the other electrons with respect to the electron that has been added or the hole that has been created when an electron is ejected. Well, now let's have a look to the experiment of the gap of several semiconductor. This is extracted from a famous paper of Mark van Schischarter, compared with the density functional theory calculation. Well, before, for the quantity related to the ground states, we had this accuracy of few percent with the experiment. Now we are off also about 50%. So DFT is not predictive here. And note that this is not a problem of the LDA. This is indeed a problem of the Kohn-Sham scheme itself. That is a theory from ground state, and this measurement does not involve excited states of the material. So from here you can understand the needs of developing theories that can access this quantity. There are several computational methods here, starting from DFT. This arrow indicate, I mean, the far from the origin, we have a more accurate method at the expensive to be very computational demanding. Here are divided by wave function based theory, at non-equilibrium with a real-time formulation, and theory that named spectral. And these are indeed the many-body perturbation theory we are going to talk about. This G here is our central quantity, that it is the green function. So again, here it is the expression of the gap in terms of the total energy. As I was anticipating before, we have all this physical process when an electron is injected or ejected from the system, that is relaxation, screening, and correlation. And we can think our systems in terms of the so-called quasiparticle. So this is a fundamental concept. We have many-body perturbation theory. The quasiparticle is our particle together with the column hole, the screening, I mean, provided by the other electrons in the system. And this is the quantity we want to model. And okay, so we need a theory that contains itself and write down the equation that provide this quasi-particle energy that, as we have seen, are contains information both of the n-particle system and the n+1 -1. This is the so-called green function can be demonstrated to contain this excitation, and given here the Hamiltonian of our system, so the kinetic part and interaction, full interaction between electron, the green function is defined that if we consider our system in its ground state at a certain time, we do create an extra electron on the system, we do propagate in time according is dynamic, this full Hamiltonian, then we will remove it at a larger time t1 and the particle removed in a different position. So we have here a function of two space, two time coordinates. And this is what is called the green function of our system. We can do the same from the whole, so for Taiwan minor of T2 and consider it the time ordering of the electron and the hole, we have the time ordered green function. And I will not demonstrate here, you can find in textbook, I will provide some literature at the end of these lectures. If we do write our green function in frequency domain, we recognize that indeed it has the pole to these two excitation that are indeed the energy difference between our system with an electrons and +1 and -1 energies. And we will have lectures on that tomorrow. Then how we can calculate this object, this is green function, this is the idea of the perturbation theory that we will see in this day. The idea is to start from something that is known and to evaluate what is not known by perturbation theory, so hoping the difference is small. So the idea is to consider the so-called non-interacting green function, so the green function of an Hamiltonian of non-interacting electrons, adding an interaction as a perturbation, and everything is not known. This is a formal definition, is put in a quantity that is our self-energy. And here we will see example of self-energy, in particular the GW approximation for the self-energy. Now I want just to point out agnostic of how this self-energy is done. This is the equation we have to solve. It's called the quasiparticle equation, and that I wrote here in blue on the left. And I just to compare in green what is the more familiar Kohn-Sham equation. As you can see at the first sight, the two equations are not that different, but there are particularity and difficulties to afford. So they look similar, but in both cases, the exchange correlation effect, I mean the big C that we have in the Kohn-Sham equation, now we have a self-energy. And the self-energy, as in the case of Kohn-Sham, contains all the many-body effect. The difference is that now the self-energy is not Hermitian, is not local, it depends from error prime, and this is also frequency dependent. So as you can see, it is a nonlinear equation because of the presence of the energy also in the self-energy and in the solution of equation, a difference of the exchange correlation potential that is local and at least in the Kohn-Sham formulation, not in generalized Kohn-Sham, so not hybrid function, and is not frequency dependence. Other difference is merely interpretation. Big C in Kohn-Sham is a potential of a fictitious system. Now, in a quasi-particle equation, the self-energy can be considered indeed the real potential felt by the system when we add or remove an electron. And the energy, the solution will be also complex. So our excitation, we have a lifetime that has a physical meaning. Here, just this is a spoiler. Let's say you will see in the next lectures how perform many-body perturbation theory. This is GW in its more simple formulation. You will see them later. This is G0 W0, one-shot calculation. calculated on top of the local density approximation, and now you can see that it reconciles nicely with the experiment of gap of semiconductors. Okay, here just I highlight the case of diamond. The agreement is perfect, but for a wrong reason. And if you're curious, we can discuss later about that. We don't enter in this detail. From a computational point of view, I want to emphasize that GW is GW, many body perturbation theory in general is very, very computational demanding, and for this reason, it's also needed a stress test for exascale computing, because of the reason I put it here. So the typical cost in system size, there is a lot of communication, dense linear algebra, and fast Fourier transform, memory pressures, and limited algorithmic shortcuts. We will see this also in the tutorial. And indeed, this is just to show that the Gordon Prize finalist of last year, 2025, so the last prize that were done, two works that received they arrived in the finalist, or that got also an honorable mention, dealt with many body perturbation theory. So I'm running a bit late probably, so I just want to introduce the code very quickly. We will take time to discuss about the code in the next hours and days. So the Yambo Code implements many body methods as a GW and Bethe Salpeter equation you will see in the last day. It is based on the basis set are the plane waves and make use of pseudo potential for the electron nuclear interaction, and that it is interfaced with several DFT code on plane wave code as quantum espresso or a Binit. This is, let's say, the general flux of a calculation. We also need a DFT simulation as an input, as input for many body perturbation theory. If you remember, you have to calculate first G naught, so the non-interacting Hamiltonian, the green function of the non-interacting Hamiltonian. You can choose your favorite, but is a good practice to start with an Hamiltonian that is not that far from the accurate calculation, so density functional theory. We do build our green function from the eigenvalue, eigenvector, conventional eigenvalue, eigenvector. We can build our green function, and importantly, the so-called microscopic screening. We will see in the next lecture by Claudia. This is the so-called density response function that is the main ingredient to build our self-energy or our Bethe Salpeter kernel. What you can calculate with the green function once you know the green function of the systems. So for emission quasiparticle photoemission experiment, you can simulate, so having access to quasiparticle and band structures of the material. This is an example of molybdenum disulfide bulk. You can calculate, for instance, electron energy loss spectroscopy or inelastic X-ray scattering spectra. Of course, you can calculate optical absorption and deal with all the physics of the excitons in your systems. This will be the topic of Thursday. Exciton analysis, luminescence. You can also calculate Furnace-assisted luminescence, as well as in Yambo with a time-dependent propagation. You can access nonlinear optics as well as time-resolved spectroscopy. What kind of systems you can deal? Well, many of them from a bulk system, complex bulk system, as here metal oxide frameworks, perovskites. You can treat defects in your system. And from 3D, you can also consider nanostructure lower dimensionality, as here an example, nanotubes or 2D materials in Yambo. I don't know if you have time, but we have special algorithm to treat in accurate way bidimensional materials. You can also calculate excited states of molecules, single molecules, even if you pay the price to use plane waves. So maybe this is not the best basis to treat molecules, but it's accessible and affordable. Yambo, it is used mainly in Europe, but also China, United States, and quite spread over the world. These are the two references describing the algorithm and technicality of the code. And thanks to the max activities in the last year has been ported in most EuroHPC machines and also in Japan, in the Fugaku machines. These are scaling tests. I will not enter in this, just to say that is able to occupy an entire pre-exascale machine, but we will dedicate a lecture by Nicola on the topic. And yeah, we are really committed also in training. These are just a list, not comprehensive of the last training events we had with also in Europe, but not only Europe, there is also a large activities in Africa and the collaboration with the institution and competence center. Okay, so about these treatise, the idea that I hope what you will learn is some theoretical foundation on linear response, GW approximation, and Bethe and Salpeter, and in then hands-on also you will delve with how to obtain meaningful results. This is an important topic when doing many-body perturbation theory because many details should be considered to have accurate results and also to know the limitation of the methods because when we talk about GW, this is an approximation and we have to know the limit of the approximation we are using and how to use the code also best practice and to exploit at the best in high performance computing environment. Well, so I'm finished here. I invite you to ask questions after the lecture, but also during the hands-on. We will be there. So you can put your questions probably in the chat, or you can, I think, take your mic. This is the problem of the day was already shown by Lucy, and some very quickly take a message from this lecture. So the density functional theory is for sure, no doubts, the workhorse for electronic structure calculation nowadays, but it is not a theory for excited states, and this is why many-body perturbation theory is still developed and used in the community. It provides accurate description of electronic and optical excitations, and the central quantity is the one particle Green function. In order to access the observables, you need to solve a nonlinear equation involving self-energy, so the interaction of the system, which is non-local and dynamical. And yes, it comes with difficulties. It's significantly more computational demanding than density functional theory. And today, I mean, in the last years, we have assisted with the advent of hybrid architecture, GPU. At least we observed the one we ported our code on GPU that really there was a factor, a large factor that allow us to treat systems, medium-sized system that was not possible to treat a few years ago. And okay, here just a sentence about the TFT tells us where the electrons are. Many-body perturbation theory tell us how they are observed as deals with excited states. Some useful link, then we can come more details, maybe put also in the chat. We have a wiki pages. Here are the where you will find the tutorial. We have a PDF, a very old PDF document, but I find it useful and it is very downloaded. It's called the cheat sheet, where you can find the what is implemented in the Yambo code in terms of the input variables. So you want to control your input file, so to have knowledge of what parameter you are change. We have a Yambo forum. You can subscribe and ask questions if you will use Yambo for your research in the future about compilation, usage, and so on. And we have set up also a Slack channel for this school. You can find at this address to ask questions during the days. And
Sorry, Daniele, about this Slack channel,
yeah.
the invitation link is not that one. I'm copying the right one in the chat of the meeting.
Thank you, Nicola. Thank you very much. Sorry, I did this morning. I probably did something wrong. And here some suggested reads, books. For instance, this book, Martin Raining, Separately Interacting Electrons, this with many body perturbation theory in comprehensive wave. There are here the seminal papers on the foundations. Several reviews appeared also in the last years, and the last two are the Yambo paper implementation. And okay, here are the sponsors. I thank you the NCC Czechia for these opportunities, of course, and I thank you for your attention. And I don't know how we want to deal with the questions, curiosity, and I will be happy to answer.
Okay, so good morning. My name is Claudia Cardoso. I'm also a researcher from the Nanoscience Institute from CNR in Modena, Italy. And in the sequence of the introduction that Daniele made, I will do a first introduction to the theoretical bases that are at the origin of the calculations that you will learn how to do with the Yambo code during these days. So I will talk about linear response theory and approximations like independent particle and random phase approximation. So you have heard the introduction about the Yambo code. So I will try to explain some of the key ingredients that will later enter in the GW and the BSc calculations. So you will hear about properties like the dielectric function, the response function, polarizability. You will hear these words a lot. And these quantities will not only enter the GW calculations and the BSc calculations that you will learn how to do, they can by themselves give some information about the materials that we want to study. So we are interested in addressing the materials interactions with an external stimulus that can be, for example, a beam of light or a beam of electrons. These interactions can be used to explore the properties of materials, notably through experiments such as optical absorption or electron energy loss spectroscopy, among other spectroscopy tools. An enormous spectra of stimulus can be explored, and their energies extend well below and well above various single particle and collective modes excitations. So in these measurements, different properties will arise from different underlying band structures, because here we will be talking mainly about solids, so we'll be talking about the band structures of materials. So we will measure different properties arising from different band structures. For instance, in metals, where you have excitations that can be intraband excitations, or you'll have different measurements if you have a semiconductor or an insulator. This means that the essential features of the band structure can be accessed by optical experiments, which can probe elementary excitations, both single particle and collective excitations. So the response of the states of a material to an electromagnetic field leads to the dissipation of this field. And this is related with fluctuations which arise in the material. So the relevant fluctuations are expressed in terms of current or density correlation functions. And they are related to the response of the material to this external stimulus. So the presence of a field may lead to electric dipoles, polarization charges, can induce currents, and consequently, to account for these modifications of the field inside the medium, we have to consider the dielectric displacement, this Maxwell dielectric displacement field, instead of the electric field that we would consider in vacuum. These two quantities are related through the dielectric function, a function that depends both on the spatial and time variables. And the dielectric function can in its turn be written in terms of this response function chi, or the polarizability that we will introduce in detail later. So, except when using very strong fields, such as strong laser fields, the response of the material, can be described within the linear response. So this means that if we, for example, expand the polarizability that encodes the response of the material to this external electrical field, if we expand it in a series that depends on the strength of this applied field, in principle, most of the phenomena we want to study, like the absorption of light, can be described by the linear term, by the first term in this expansion. So they can be described within the linear response. Okay, so for wavelengths that are larger than the atomic spacing, we can consider a macroscopic average of these microscopic properties, like the dielectric function. And this macroscopic dielectric function is related, for example, with the diffraction index, and describes how an electric field or electromagnetic wave that propagates in a medium is attenuated by that medium. This can be used to study the properties of materials, and notably, it can be used in the optical absorption spectroscopy. So in optical absorption measurements, a sample is shown with light, and part of the beam will propagate through the sample and will be absorbed differently for different wavelengths. This absorption gives information about the optical excitations in the material, and is related with the imaginary part of the macroscopic dielectric function. So the dielectric function, as you'll see, is one of the fundamental properties we'll be talking about. Another important experimental probe is the electron energy loss spectroscopy. It is a form of electron spectroscopy in which a material is exposed this time to an electron beam with known and narrow range of kinetic energies. And some of these electrons will undergo inelastic scattering, losing energy and changing momentum. And the amount of energy loss can be measured via electron spectrometers and interpreted in terms of the excitations, both single particle or collective. In the case of fields, the spectrum is related to the imaginary part, but not of the dielectric function, of the inverse of the macroscopic dielectric function. And this is a detail that will be important, as you'll see later on. So one of the differences between these two experimental probes is that they actually deal with different excitations. So in these experiments, the electric field propagates through a medium along a particular propagation direction. So we can decompose our displacement field and the electric field, and of course also the dielectric function in components that are parallel or longitudinal or perpendicular or transverse to the propagation direction. So the dielectric function is the function that connects the displacement field to the applied electric field, and therefore has to be written as a tensor. And the longitudinal and transverse components of the field might mix. So these terms can be different from zero. And this, in principle, depends on the symmetry of the system. So if the system has a high symmetry, these terms here will be zero. This is important because different experimental probes will access to two different parts of this dielectric function. For instance, the optical absorption will probe transverse excitations, so this term here, while the electron energy loss probes longitudinal excitations. So in principle, we would have to develop a different framework for these two experimental techniques. But what happens is that since the speed of light exceeds substantially the velocities of the various excitations in solids, we can mostly work in the optical limit. So in the long wave limit. And in this limit, we see that the longitudinal and the transverse components of the electric function are similar. So we can use just one of them to describe, for instance, both absorption experiments and electron loss experiments. And this is convenient because if we consider the longitudinal dielectric function, we can, this dielectric function can be expressed in terms of scalar potentials instead of the electric vector fields. And in particular, the scalar potential, it will be defined by the density, the electronic density of the material. So we have a framework where the electronic density is a fundamental quantity, and this, for instance, correlates with the use of density functional theory calculations, where also there what we compute is the density of our system. So from now on, we will focus on computing the longitudinal components of this macroscope. So the purpose is to compute the longitudinal component of a macroscopic dielectric function. So how will we do that? We can perturb an electronic system with an external field or an elastic scattering with charged particles to gain information about the system through the dielectric function. To calculate the dielectric function, we will first define a microscopic, so we'll develop a microscopic formulation to describe the response of our material to this external perturbation. Then we will write a density response function. Then these are all microscopic quantities, and then we'll have to link the microscopic and the microscopic quantities to obtain a quantity that can be compared with experiments. And then we'll compute them within simple approximations like independent particle and the random phase approximation. So we start with the definition of the microscopic definition of our system. The system is described by an Hamiltonian that can be divided into parts. This is the case. So we have this H0 that is, let's say, the Hamiltonian of our unperturbed system, and that contains all the interactions in the system. And then we apply an external perturbation. For now, we'll write this external perturbation as generically as a product of a field and an observable P. And we'll see later that these quantities correspond to the electric field and the electronic density. Then we will need to evaluate the expectation value, to know how to evaluate the expectation value of a generic operator O at time t. And for that, we start by writing the Schrödinger equation that we have here. So this is the definition of our microscopic system. So in the Schrödinger representation, the time dependence is carried by the state vector. But since we have an Hamiltonian that is separated into terms, this, in particular, this H0 that does not depend on time, it is more convenient to work in the interaction picture. So we, instead of working in the Schrödinger picture, we work in the interaction picture, and we can obtain our state and our Hamiltonian by applying these exponentials here that now carry some of the time dependence. So now our operators will carry some of the time dependence. And the time evolution of our states is now given by this expression here. And to know the state of our system at a certain time, we will have to integrate this equation. Okay, so sorry. Okay, so this is the equation from the previous slides. We have to integrate this equation to obtain the state in the interaction picture. And now we want to solve it within the first order to the perturbation. So what we do is that in this equation, we will replace this psi t prime with this same expression here. Can you see the pointer? Yes. Okay. So we obtain this second expression. So here we have this same expression here applied to phi t prime. But since we just want to consider terms in first order of our perturbation, we cannot consider the second term here. So at first order in the external field, we have this expression here. Our phi t is approximately given by the states at an initial time t0 and a term that applies our external perturbation to the same states at time t0. So we can simplify the expression in this manner here. So again, this is the expression from the previous slide. And as we said, we want to compute the expectation value of a generic operator O. So in this case, we have our state. So here we come back to the Schrödinger picture through these exponentials here. And in the Schrödinger picture, we use the expression we derived in the previous slide and the expectation value. So we have to use the expression both in the brackets, in the bra and in the cat of this expression. So the expectation value is then given by the expectation value of the same operator at time t0, and the second term that is a commutator of our external potential and the observable we want to compute. So we have a commutator because we have applied twice the expression we derived because we have a bracket, a bra and a cat here. Okay. So the next step is to express, we want to know how the system responds to this external perturbation. So we want to know the difference between our observable computed with the perturbation and without the perturbation. So we want to compute this fluctuation here. And we have said that our perturbation that we previously wrote as a generic, so our perturbation, we have previously written it as a generic field and an observable of the system. So a fluctuation in general is given by the expression we have derived before, but we are subtracting the expectation value at time t0. So we'll only have this term here. If our perturbation, as we said, is a applied electrical field multiplied by the density, and the fluctuation that we want to compute, the observable that we want to compute is again the density. So the fluctuation in the density is given by this expression that has a commutator between the density operator applied to our state, our ground state. Okay, so we have computed a fluctuation and we now want to compute a response function. And a response function is like the derivative of an observable with respect to the perturbation that we want to compute. So we have the expression here from the previous slide, and our response density response function is the derivative of the density with respect to the field, to the applied field. And this is convenient to write, to do a Fourier transform from the time t to the frequency, because this will allow us to relate this expression with the energies of the system. So we do a Fourier transform of this expression and we introduce a completeness identity between these two operators, and we get what we finally get the expression from for our response function, for our density response function. So, and this expression here that is called the Lemon representation of the response function. And we can see that the response function that will play a very important role. So this is like the main quantity we want to compute for our system, has a form that has poles So the denominator will be 0 for energies that coincide with the difference of the between the excited and the ground state. And in the numerator, we have these density matrix functions that relate, again, the ground state to the excited state. So these excited states appear here because we have introduced here this completeness identity between the two density operators. So what have we done so far? We have written a microscopic description of our electronic system that responds to an external perturbation. We have considered the contribution of this perturbation to first order, and we have computed the microscopic density-density response function. So now we will introduce other microscopic ingredients that will be important in our calculations, and this will be the reducible response function and the microscopic dielectric response. So in the, let's say, the many-body perturbation theory language, this chi is called a reduced response function or reduced polarizability, and is useful to introduce the irreducible polarizability. And this, so while the reduced polarizability connects the density fluctuation with the external applied potential, the irreducible polarizability connects the fluctuations in density with the total potential. So what is the total potential? Is the sum of the applied potential and the fields induced inside the material due to the polarization of the electrons or due to the screening of the electrons as a response to this perturbation. So the reduced and the irreduced polarizabilities can be related using this relation of the fields in what is called Dyson equation for chi. So this is a closed equation that relates the polarizability, the reduced polarizability that appears here and also in the size of the equation to the irreducible polarizability that appears here. So for now, I will leave it like this. The other ingredient, microscopic ingredient that I would like to introduce is the microscopic dielectric function that we have talked about several times. So by definition, the microscopic dielectric function connects the external potential, so the applied potential, to the total potential. And this encloses information, again, on how the electronic system reacts to the perturbation, so how it screens the electric field, and is, of course, related to the reduced polarizability and the reduced polarizability. So you see that there is a simple relationship between the inverse of the dielectric function and the reduced polarizability, and between the dielectric function and the irreducible polarizability. So these are all microscopic quantities, and now if we want to compare these quantities with measurements, we will have to perform a macroscopic average in our system. So this Again, we are dealing with solids and we are considering periodic systems. So the microscopic, so we will take into account the periodicity of the system when doing this microscopic average. Microscopic average is performed, so we are considering a long wave limit. So we say that our applied field applied field very slowly within or when compared with the size of the unit cell. So these external quantities that are related with the applied perturbation have slow variations, but the total ones that encode the reaction of the system to this perturbation very rapidly within the unit cell. So the macroscopic average is performed over distances that are small with respect to the wavelength, but are large with respect to the size of our unit cell. So we have derived an expression for the, so if you remember, the experimental probes will measure quantities related either to the inverse or to the dielectric function. So we are interested in computing from the expression that we had for chi, for the response function. We are interested in computing the dielectric function, and particularly the macroscopic dielectric function. So since we are dealing with periodic systems, it is convenient to perform this average to Fourier transform not only the time variable, as we did before, but also the space variables. So the response function in the reciprocal space now depends on a momentum k, and is given by matrix elements that depend on these G indexes. So the G indexes are the reciprocal lattice vectors, while Q is the momentum in this reciprocal space. And the inverse of the dielectric function that we have shown before, so in the reciprocal space, is given by this expression here. Again, it depends on two G indexes that are the reciprocal lattice vectors. So we are doing this because we are always thinking about periodic systems. So we want to do a macroscopic average of, let's say, a generic potential. And this microscopic quantity, since it is periodic, can be expressed in terms of block functions. So it can be expressed. So this quantity in real space can be expressed as a sum of these phase terms here, the sum in Q, and then a sum on the reciprocal lattice vectors. And if we perform this sum of this part here, the sum in G, we'll have a quantity that is periodic, that has the same periodicity of our lattice. So this is the idea of the block functions. So to know what is the macroscopic value of this VQ potential here, periodic potential, we'll have to perform an integral over the cell. So we have here the potential written as a sum of G vectors, and we see that the only dependence on the position is given by this exponential here, and this will give origin to a delta function. So our macroscopic element of this potential is, in practical, given only by the G equals 0 component of our microscopic potential. So then our total macroscopic potential will be just given by the sum in Q of this term with G equals 0. So what we are saying here is that when we go from a microscopic quantity to a microscopic quantity in the reciprocal space, this is equivalent of taking only the element that depends on G equals 0. So let's now look at the dielectric function. So we have an external potential that is related to the total potential through the macroscopic dielectric function. So in the reciprocal space, so the Q term of this expression is given, so the periodic part is given by a sum over G prime of this expression here. So the macroscopic average that is given, as we said before, by the G equals 0 term. In this case, we have to be careful, because even if we take the G equals 0 term on epsilon, we still have, since epsilon has two G indexes, we still have a sum on G prime. So when we are considering the macroscopic average of epsilon, this is not simply, we cannot simply take the 0 term to get the macroscopic average. So why is this important? Because we see that, for instance, if we, instead of thinking of the dielectric function, and we take the inverse of the dielectric function that relates the external potential with the total potential, since the external potential is a macroscopic quantity, in itself it has only the G equals 0 component. So let's say the macroscopic average of the total potential is given, in fact, by the 0 component of the inverse of the dielectric function. So this does not happen when we are talking about the dielectric function. So we still have a sum over G's to do, but when we are talking about inverse of the dielectric function, we can directly just take the head of the matrix, so the 0 G component. So why is this important? Because if we go back to the examples of the experimental probes that I was talking about, we have that the optical absorption is given directly by the dielectric function, while the electronic energy loss is given by the inverse of the dielectric function. So we have to be careful and to say that the macroscopic dielectric function is the 0 term of the inverse of the dielectric. So we have to do this inversion before we take the 0 component. That is different from taking the inverse of the 0 component. And in the case of the yields, electron energy loss, it's simpler because we'll have access directly to the 0 component. So what does this mean? Why have I done all this very long speech about these macroscopic averages? So when we ignore this difference and we want to compute the absorption spectrum through the calculation of the dielectric function, and we ignore this difference, so between taking immediately the 0 component or doing the inverse direction, what we are saying is that we are taking into account or not the inhomogeneity of the system. So if the system is homogeneous, these two quantities are the same. But if there is inhomogeneity, they will be different. And this can be seen in the calculations of the imaginary part of the dielectric constant, where we take into account what is called local fields. So when we take into account the local fields, we are doing the proper macroscopic average. When we don't take them into account, we are skipping that sum on G vectors. And we can see that for a bulk system, this is beryllium, considering or not the local fields doesn't have much effect because a bulk system is more or less homogeneous. But if we do calculations for the beryllium atom, we see that we'll get completely different results by considering or not the local fields. And here there is another example of germanium nanowire, and we can see that in the periodic direction, if we consider or know the local fields, we'll have very similar results. But if we consider a non-periodic direction, it is important to do the proper macroscopic average. That can be computational demanding, so it would be much simpler not to do it. Okay. So we have a Lemon representation for our response function, and we have a way of computing the inverse of the electric function from this response function. And we have then to take care of this macroscopic average to obtain the macroscopic inverse the electric function. So how do we do in practice these calculations? So we have this expression for the response function, but now we have to determine all these elements in the expression. And for that, we have to define our Hamiltonian, the Hamiltonian of our system. And the simpler Hamiltonian that we consider is an independent particle Hamiltonian. So we can take, for instance, the Hamiltonian that we will diagonalize in a DFT calculation. And in a first approximation, we can say that the R3 potential and the exchange potential depend not on the final density of the system, but on the unperturbed density of the system. So this is our approximation. We have a single particle Hamiltonian that we have diagonalized. We have the single particle energies and our block functions. So we know how to write the density operator, and the density is just given by the square root of the block functions multiplied by the occupation of each state. So we can compute in this non-interacting approximation an expression for the response function. And from this, we can compute our final dielectric function. That is written here. So here the dielectric function is written in real space. So what we can see is that the electric function is a function that will have poles in the energy differences between conduction and valence states, as we have seen before. And in the numerator, we will have the dipole moments between these two states. So this is the dielectric function at the independent particle approximation. And this is obtained also non-considering these local fields, so not performing this proper average, macroscopic average that I was talking about. So the next simplest approximation is what we call the random phase approximation. That is very similar, but now we consider the local fields. So in the R3 term, we now have the density of our system, and we'll have consequently expressions for the response that are a little bit more complicated. They will depend on the G indexes, and they will have these exponentials here. And so you can see just by this hand-waving explanation of these expressions that already going from the independent particle theory to the random phase approximation, we have a jump in computational complexity. So we'll have some extra operations to do. So summarizing, we have started by saying the relevance of computing the dielectric function because it gives us access to properties that are measured in experiments such as optical absorption experiments or electron energy loss. We have defined a microscopic framework to describe our system. We arrived to an expression for our response function, and we computed our response function within two approximations that were the independent particle approximation and the random phase approximation. So just to finish, I show here a calculation done with this, a calculation of an absorption spectra, so the imaginary part of the macroscopic dielectric function, calculated within RPA, compared with the experimental results. And this is an apparently very simple system that is bulk silicon. And as you can see, the RPA calculation, this calculation in blue, doesn't reproduce very well the experimental results. So the discussion of why it doesn't reproduce well the experiments, it's the topic of all this course. So you can see that other calculations at a higher level that are, for example, the GWRPA or the BSE calculations can be used to compute this dielectric function, and they get closer to the experiment. So, for instance, here the BSE calculation will give the correct experimental result. So, this, I just want to say that this doesn't happen for all the systems. There are systems that already at the RPA level are well described. But even if the response function calculated at RPA level does not describe exactly our dielectric function, it is a fundamental, it is a key ingredient in the methods that you will learn in the next lesson. So in the GW and the BSE calculations, you will go through the calculation of this response function. So I will end here, hoping that I didn't take too much time. And if you have questions, or I will leave you time for questions.
Meantime, thanks a lot, Claudia, for the presentation. This is Andrea Ferretti, still from CNR Nano, Modena, Italy, and today I'm following on some of the subjects and the remarks that Daniele has made yesterday. So he gave a bird's eye view over the whole spectrum and of topics. Now we are going deeper into some details, especially the Green's function theory and the foundation of the GW approximation. And in order to do this, I'll start from a theoretical description of the ARPES, so photoemission experiment, because that introduces some of the needs in terms of theoretical description that we need to plug into the theoretical framework, and then connect that to the theory of Green's function, and eventually introduce the GW self-energy as an approximation to the theory, basically discussing pros and cons, successes and failures or drawbacks. Okay, so let's start from the introduction of ARPES. This we've already seen yesterday. Still keeping in mind the theoretical framework we would like to build, it's key to make a clear distinction between processes that determine an ionization of the system, like, for instance, direct and inverse photoemission, or processes like optical absorption that keep the system neutral, exactly because in the first two cases, we have the involvement of so-called charged excitations, so excitations upon ionization. In the latter, instead, we don't have any excitations, and we deal with the neutral excitations. And the key reason to keep this in mind is exactly that the theoretical framework, the mathematical objects needed to describe these two aspects are somehow different in the formalism I'm going to present here. Here is again the sketch of ARPES to make it clear on, from the experimental point of view. The idea is that there are incident photons of which we could control the frequency, but also the polarization or the angle. And what we measure is the kinetic energy of the outgoing electrons, again, including also the angle at which they are emitted and possibly and or spin. And somehow this allows to access the so-called electronic band structure. Here is a sketch. Probably you're not seeing my mouse, right? Yeah. So on the left, we see a sketch. So we see a non-interacting situation where we have some deep states that are not dispersive, and then some parabolic bands with the Fermi level cutting through. And upon ionization by means of a photon of energy h nu, basically we see a mapping of the deep states and of the valence band until the Fermi level. Of course, since we are extracting electrons in this approach, we are not addressing empty states. And if that is a cartoon on the left, on the right, we have some realistic experiments run at the synchrotron. This is graphene on nickel. And we really see the dispersion of the band structure and of the bands of nickel, bands of graphene, the broken Dirac cone. So there are all the features we typically describe within electronic structure theories. The process of photoemission can be modeled, and for instance, using Fermi golden rule. So we have a photoemission current J of k, where k is the momentum of the outgoing electron. There is a perturbation that is treated classically or semi-classically as a vector potential. This is the description of the incoming photon. The outgoing electron has kinetic energy k square half, and then we have the leftover, so the system that is left with one electron less, where we have an excitation from the ground state to some excited states. Actually, this is not the whole story. In principle, the final state is definitely more complicated to deal with, since it needs to account for the whole process, and needs to account for we can call it the entanglement of the outgoing electron and the remaining ionized system. But here we want to do one step more in the modeling. That is, we want to just split the process into steps, and here is the famous three-step model, where basically we first as the absorption of the photon and the excitation, and then the excited electron goes through the surface, and so let's say moves within the material, and then goes through the surface into vacuum. In a sense, out of this, one could define what are the so-called photoexcitation intrinsic losses that are those happening in the first step. Then we have also some extrinsic losses, so energy losses, for instance, that happen when the electron propagates in the samples, and then eventually also some extra matrix elements in transmitting through the surface. And here we are mostly interested in the description of step one. So with this in mind, basically, or with this approximation, one could make the so-called sudden approximation. That is, if the outgoing electrons are fast enough, we can neglect in the final state most of the complication of the scattering of electrons within the material, and then just describe the final state as the excited state, and with n-1 particle left in the system plus a free electron with momentum k in vacuum. And if one, this amounts to basically neglecting the so-called extrinsic losses, all the dynamics within the material. And what we are left with is that the photoemission current just becomes this object here. These deltas are matrix element of the vector potential, but importantly, we have this quantity A that is the spectral function related to the Green's function. Here is an expression of it, and we see that this quantity A involves a delta with the charged excitation epsilon s, that is the conservation energy delta times matrix elements involving the n-1 excited state coupled to the ground state with n particles via a field. So these are really the matrix elements describing the ionization from the ground state to an excited state with n-1. And as we will see, this is a forward pointer. This object here is directly connected to the Green's function. It's the imaginary part of the Green's function. And this is why in this nice review by Damascelli and co-workers on the ARPES experiment, it is clearly stated that the connection, the evolution of the ARPES experimental technology also has a counterpart in the evolution of theoretical frameworks able to describe the Green's function, because the two objects are really tightly connected. And so somehow we arrive at the introduction of the key mathematical object of this presentation, that is the one particle Green's function. This is the formal definition that we have already seen yesterday. So this is the ground state expectation value of a time-ordered product of fields that somehow describes for positive times the evolution of an added electron added to the system, and for negative times the evolution of a hole added to the system. And we take the amplitudes of adding the electron, the hole at one point, and looking at the probability of finding it at a later point in a different space point. Okay, so basically using, now we dig into some of the mathematical properties of this object. So far, everything is exact. This is a mathematical object we can define for the interacting system. And so by using the completeness of eigenvectors with n+1 and n-1 states, the Green's function can be written in this form that is also called Lehmann representation. So this is a sum over poles. The poles are total energy differences involving charge excitation. So it's the difference, for instance, for, let's say, occupied states of the ground state energy at n and the excited state n-1. And for, let's say, the empty channel, or for empty states, this is the difference between excited state with n+1 and the ground state at n. And these objects here that are genuinely many-body quantities, total energy differences out of many-body quantities, play the role of the eigenvalues in the non-interacting picture, in a mean field picture. The orbitals at the same time are described in terms of the amplitudes, again, of the ground state matched with n-1, n+1 excitations via a field operator. And these are called Dyson orbitals or Dyson amplitudes. And these play the role, these are the actual many-body definition of single particle orbitals. And as you can see, so out of this definition here, if we go back to our description of photo emission, these amplitudes, though in a different basis, are exactly those that we have here in the definition of the spectral function. So we are really basically tightly connected, as I've anticipated. And here is the formal definition of the spectral function. Somehow we can take the imaginary part in operatorial sense of the Green's function, so 1 over 2i g minus g dagger, then there is an extra factor pi for normalization. This sign of mu minus omega stems from the fact that we are dealing with the time-ordered Green's function. It's just a technical aspect, but what is important is that out of the spectral function, we can rebuild the Green's function. So we have this expression of the Green's function in terms of the spectral function. And you can clearly see that this is pretty much, this is a Kramer's chronic or a Hilbert transform in the more general sense. And the spectral function really is the source of this Green's function. So all the information encoded in the Green's function is actually encoded in the spectral function. Spectral function that eventually we can write in terms of Dyson orbitals, as is written here. So is a frequency dependent density matrix out of Dyson orbitals, or in a local form, this is the spectral density. We obtain the spatial resolved density of states. And this is, again, the proper many-body definition of the local density of states. That is a key and common concept in electronic structure methods. So we can go a step further, and if we introduce the Dyson equation, if you want, it's enough to introduce the self-energy, as Daniele did yesterday, as an alternative way, even non-perturbatively at this time. So we haven't mentioned here yet a method to introduce the self-energy, but the second equation here from the top could be taken as the definition of the self-energy. So the self-energy is that dynamical operator that I can use to exactly compute the interacting Green's function. So what is the correction we need to add on top of each knot to compute the interacting Green's function? So this could be a practical functional definition of the self-energy. So for discrete states, out of this definition, one can obtain the following expression for the Dyson orbital that is in the form, this expression here in the framed, that is in the form of an eigenvalue problem, except the fact that the self-energy now depends on the eigenvalue itself. So this is the mathematical jargon, a nonlinear eigenvalue problem, because of the frequency dependency of the potential induced by the self-energy. Also, we know that the normalization of the F orbitals need not be 1, but is rather Z as defined according to the derivative of the self-energy at the epsilon S eigenvalue. So here is a main key point. So this, though this Lemon expression for the Green's function really looks like Green's function of a non-interacting case, here we have two main differences. One is that the number of orbitals is much larger. In the non-interacting case, basically we have just one orbital per electron. Here, because of the size of the many-body space that is involved, that is much larger than that of a single orbital case, we have many more options for Dyson orbitals, Dyson amplitudes to be non-zero. So this S sum here runs over a multitude of orbitals, and depending on the way we describe the basis set, that could be really an infinite number of states. Second point is that these orbitals cannot be orthogonal, so somehow they are overcomplete among themselves. They cannot be orthogonal, and they are not normalized. So these are the main key differences with respect to the non-interacting case that I'll further discuss later on. There is another exact representation for the Green's function. So if we look at omega here, or just its extension to the complex plane for frequencies, one could think of invert the Dyson equations by diagonalizing the problem, and the self-energy is in general non-Hermitian. So what we obtain is this other representation involving left and right eigenvectors, sorry, with these frequency-dependent eigenvalues. So these two representations are exactly identical for discrete states when we are on on the real axis. Somehow the two coincide, but this alternative representative that is still exact stresses that if we just want to retain the main features of the Green's function, one should search for poles that are given according to this condition here, and this somehow says that the multitude of poles that are all on the real axis we've seen in the lemma representation can just coalesce into single poles that are farther from the real axis. Here the math becomes extremely complicated in so when going to the thermodynamic limit, because in the before the thermodynamic limit, when all the states are discrete, this is not a big deal. When the states becomes continuous, somehow there are branch cuts that form, and then the analytical structure of the Green's function becomes much more involved. Because of branch cuts, there could be the function could become polydromic with multiple Riemann sheets. So the math and the analytical structure become extremely complex, but this is not what we are interested in. What we are interested in is pretty much this picture here. So somehow in the left, we see in the left side, we see the Green's function before the thermodynamic limit, where we have a multitude of Dyson peaks that get together and clusterize to form some sort of structures. And out of the second representation, we can approximate or just describe the main structure of the Green's function according to single poles that are just shifted away from the real axis. The second form is more convenient for a direct physical interpretation. Somehow this says that the energy of the states that now we call quasiparticle states acquire, because of interaction, a finite imaginary part that once translated into real time becomes a lifetime or a decay. These so mathematical aspects are discussed in the work of Behnam Farid. There are a number of seminal papers from this author. So all of these aspects, I think, are nicely discussed in some of his work, in particular these two here. Here is a more general picture. So what is the physical content that the self-energy could bring. Here we put ourselves in a simplified picture where the self-energy is assumed to be diagonal on the basis of the H-naught Hamiltonian, such that the Green's function, the Dyson equation, become a scalar equation. And if we do a Taylor expansion around the quasi-particle energies, we see somehow that this one delta-like peak of the non-interacting spectral function just is shifted and by the real part of the self-energy and acquires a broadening, that is the imaginary part of the self-energy at its energy, and also becomes renormalized. So it's not normalized to 1, but its spectral weight is reduced because of the Z renormalization factor that somehow hints at the fact that since the spectral weight needs to be conserved, there are also other structures that arise like these satellites. Of course, here, because of the Taylor expansion, the satellite is dropped because we are just discussing the frequency behavior of the spectral function close to the quasi-particle peak. But these are the key physical ingredients we can extract from the self-energy. And here is somehow a summary picture. So many body corrections or many body features to the spectral function, to the Green's function, include the renormalization of peaks, both in terms of energy position and in terms of spectral weight, the introduction of lifetimes, that is a broadening of the peaks, and the presence of satellites. And all of this is described by the dynamical and non-Hermitian nature of the self-energy. I think that this is the key concept. Basically, there's no way we can describe these features using a static potential as the Coneshan potential, and that's why we need to introduce a dynamical non-Hermitian self-energy. Okay, so let me get, these are all exact properties. Let ourselves get into ways to compute the self-energy. And besides the classical many-body perturbation theory, where Feynman diagrams are developed in 1965, Lars Hedin introduced an alternative approach where he added to the interacting Hamiltonian H0 here perturbation sampling field that he used to introduce the concept of a response function, eventually letting this field going to 0 by the end of the calculation. But that allowed to derive a set of 5 equations that importantly are closed and allow one to compute the exact interacting Green's function. So somehow, according to these are called Hedin's equations, and according to this formulation, we have a set of integral differential in a functional meaning set of equations. Let's quickly look at them. The first one is the Dyson equation that we've already seen. Then the second one is also let's say a redefinition equation for W, that is the screened interaction. This is the key concept introduced by Hedin. And the second Dyson equation just connects the Baer-Coulomb potential via the polarizability of the system P to W. So somehow is the definition of W itself. And then P and sigma, that are the 2 key quantities in these 2 equations, are defined in terms of polarizability in terms of the vertex gamma, that is the key hidden and complex quantity here. The self-energy is just GW gamma with suitable index connection and topology, and the polarizability is GG gamma. Remarkably, GG without gamma is the polarizability of a non-interacting system. And gamma is a product of deltas that just gives this non-interacting flavor, plus what? Plus the functional derivative of the self-energy with respect to G. And this is the key quantity. This is also, if you think at the R3 potential, this is somehow, if the self-energy is the R3 potential and G is basically a density, this would be the Coulomb kernel. So this sigma in this G, that is a 4-point quantity, is also identified as an effective many-body interaction, okay? The 4-point with frequency dependence, so with all the complexity cascading. So these are exact. They are not easy, clearly, to solve even numerically, because this is not regular differential equation, it's functional differential equation, but approximations can be made. So here I'm just making a comment about the fact that Dyson equations actually, when iterated, could be seen as the formal. So the solution of a Dyson equation is formally the solution of a geometric series without the need of a convergence radius. So as I stated, all the complexity just comes from the blue term in the vertex that then propagates the polarizability and to the self-energy. And in the GW approximation, somehow these blue terms are dropped. So we just retain the non-interacting bit of gamma, so delta delta, that then propagates to the polarizability that becomes GG and to the self-energy that becomes GW. And this is indeed the way the GW approximation is introduced. So somehow this means that the polarizability is, so vertex is treated as the non-interacting one, polarizability is treated at the independent particle level, that then with the Dyson equation for W becomes treated at the RPA level in the reducible level of theory, and the self-energy becomes GW. That is what gives the name to the approximation. And here are, if we convert the self-energy into diagrams, this is what we obtain, just G times W, and so we can expand G, so W in terms of polarizability bubbles, and so we obtain this infinite series of diagrams. And importantly, so we've made some significant approximations to begin with. That is, we have neglected the difficult part of the vertex. So GW is definitely not the whole story. And out of already these first diagrams, we can already see that there are clear diagrams that are missing. And the first one is this second order exchange that is actually not there. And here is another comparison. We can see or think of GW as a dynamical extension, including dynamical screening of the R3 Fox. So G times V in this language is the R3 Fox self-energy, is the non-local exchange. And basically, if we replace V with W, we obtain the GW self-energy that comes with all its dynamical nature. And another connection is with the second Bohr self-energy that is also connected to the MP2 energy correction from quantum chemistry. So somehow MP2 is working on top of R3 Fox, is a perturbative correction to the total energy. That is obtained in terms of a self-energy with this set of diagrams here. So just first order and second order diagrams. So somehow this second born self-energy stops at second order. GW goes to infinite order but drops some of the exchange terms. And again, here probably we need to think at different approximations with different validity and accuracy in different regimes. So for instance, for very localized electrons, probably second order exchange diagrams are relevant. For very extended or metallic system, the complete summation of the RPA bubbles is instead more relevant. So how does it work? It works indeed, and so somehow GW is the workhorse in the field here for solids and gaps, but also molecules. Recently, also the GW100 set has been introduced. So there is an extended set of benchmarks, at least for molecules across different codes, different implementations, and so on, but also not only for molecules, but also for solids. But so as I mentioned, GW is not the end of the story. So first of all, GW, because of the RPA polarizability, suffers of self-interaction, in particular self-screening. So while the R3-FOC in principle is exact for, in principle and in practice, is exact for one electron cases, GW is not exact for one electron case. So GW, because of W, introduces some screening even in one electron case. So this is the first remark. And all of these can be corrected by so-called vertex corrections, that in a sense is a global word for global naming for whatever goes beyond GW. And here are also some examples of our own research of some inclusion of vertex correction. That is exactly, you take the vertex function and just plug in some approximations for this sigma in the G. In this case, for instance, which the time-dependent R3-FOC vertex that is similar to having a BSC vertex. So if one were including static screening, this would become a BSC vertex included into the calculation of the self-energy. This is the way it works for atoms, and typically there could be missing satellites, so missing replicas of the satellites, because GW is first order, and satellites with the wrong energies. If one is interested in satellites, typically G0, W0 plus cumulant is a better approximations. There is also a whole discussion about working with G0, W0 or fully self-consistent GW. This is a very recent paper. There are even more recent ones discussing the point. This also has to do with some numerics, because performing fully self-consistent GW is rather numerically complicated, so you need to have full control over the approximations. Here is a nice work from the group of Lucia Reining and co-workers from 2011, going beyond GW using a cumulant expansion, and this is a way to fix the position and the appearance of replicas in the satellite. So if one is interested in satellites, the inclusion of cumulant is definitely something that needs to be considered. Plus also here there is a modeling of extrinsic losses added to this photoemission current. And here is another example, closer in time, so later work of the same group, where not only GW plus cumulant, but also electron phonon coupling is added plus extrinsic. And you see a very nice agreement with very recent and accurate measurements of R best done at the synchrotron. And with this, let me thank you for the attention. I'm very happy to take questions, if any.
Okay.
So maybe I can go on with the
Yes.
presentation.
Yes, please.
Yeah. Thank you, Andrea.
You're welcome.
So hello, good morning, everybody. I'm Giacomo Stessi. I'm also from CNR Modena. And today I'm gonna talk about GW calculations more in details. In the case of, in particular, I will enter the algorithm and approximation that are commonly used in calculation with the Yambo code, but in general with also other many-body codes, and there's a typical standard which GW calculation are done. So as Andrea was talking before, the many-body techniques are used to improve on, if you want, the limitations of FT, since FT is a ground state theory. And the idea is we want to explore excited state properties. Let it be, for example, as Andrea was saying, photoemission or inverse photoemission. We want, in this case, to probe respectively occupied and unoccupied states. And this allows not only allows to reconstruct the band structure of a material, and allows also to correctly determine for example, the band gaps that at the FT level are underestimated. And okay, this is a plot for certain materials, and we see that in general, so GW agrees very well with the experimental results. For example, in the FT, there is in certain cases, for example, let's look at the case of germanium, where the system is from the FT level is found to be semi-metallic, whereas in reality is a semiconducting material. And the GW techniques allow to correctly evaluate the quasi-particle energies. And this is a typical plot I'm showing here of a GW calculation in purple compared to the DFT result in black. And we see that the GW calculation leads to a widening of the band gap, and the GW energies are in purple are at a lower energy in the valence band, at a higher energy in the conduction band, and this is the typical behavior for a semiconducting material you would expect. And in particular, if we want to evaluate correctly the energies here, what we need to correctly assess is the spectral function A, that as before was spoke about, is strictly connected to the propagator G, in particular to the imaginary part of the propagator. And this, if we want the fundamental gradient, we need to correctly assess in many-body calculations. And okay, the correct formalism to which this would be determined is within the Edin's equation. This is a set of closed equations that are formally corrected. And for what concerns our case here, we will work within the GW approximation that, as Andrea was saying before, basically starts from Edin's equation, and the idea is to replace the vertex. Well, if you want to replace the vertex, approximate the vertex to being exactly equal to 1, and so we kind of skip one passage in the pentagram. And so from the polarizability chi is just computed in the RPA approximation, like minus I G times G. From the polarizability, we can compute the screen potential W by solving the Dyson equation. Then from W, we calculate the self-energy sigma, and ultimately, so we calculate the propagator G as G0 plus G0 sigma G. And this is a set of self-consistent equations, and the typical starting point, one starts from the propagator G of coming out from ground state theory, and the common choice is typically FT, but obviously other choices are in general possible. But here we will suppose that this is the case. We start from PFT calculation. And if you look at the Dyson equation, G, we see that, okay, Dyson equation is the single particle propagator, and then we have to sum the contribution originated by the self-energy. And the self-energy can be seen, if you want, as a frequency-dependent potential that is perturbing the single particle propagator. But the single particle propagator has been determined from DFT theory, so from a connection Hamiltonian. So we can suppose that also the eigenfunction and eigenvectors of the pseudo-connection Hamiltonian, including the self-energy, will respect this equation here. So basically, we can imagine that the connection Hamiltonian psi, connection Hamiltonian times its the eigenfunction. Then we include the GW self-energy, and then we remove the exchange correlation potential that used at DFT level that led to wrong values of the quasi-particle energies. So basically, we replace the exchange correlation potential with the correct non-local correlation potential that, as Andrea was saying, generally depends on the frequency. And this, and then we can ultimately, if we are able to solve this equation, determine the quasi-particle energies. Most of the times, however, this equation is rather complicated to solve, and in general, an approximation that is commonly done falls within the so-called G0W0 approximation. And the idea being that the quasi-particle wave function and the connection wave function are not too dissimilar. So we actually approximate the quasi-particle wave function with the connection wave function that have been determined directly from DFT. And so we can directly calculate the quasi-particle energies from the connection energies, and then adding the, if you want, the correction that is provided by the connection potential. Well, sorry, by the self-energy. So ultimately, so calculating this this quantity here. And if we refer again in the case of graphene on top of nickel, we see that the results are able to capture the correction provided by the self-energy, and not only the quantities now acquire also an imaginary part, so a finite line width, due to the fact that the sigma is in general a complex quantity. We respect instead to the connection potential is will not feature any extension of the line width, since it will just feature a series of Dirac delta. And if we now look at the equation of G0W0, so this is the set of the equation. So basically the Din's equation of G0W0. So the vertex has been replaced by 1. The polarizability chi is calculated in the RPA approximation, just as a product of the irreducible of the propagator G0 built from the connection energies. W is calculated as the bare Coulomb potential, then you multiply, then you solve the Dyson equation. So V times the irreducible polarizability times W. Sigma is the self-energy, is the GW self-energy, and so and the Dyson equation. When we deal with this calculation in Yambo, there are two ways in which we can represent these quantities. We can either represent the quantities in the plane wave basis set, or we can represent this quantity in the connection basis set. And these the two quantities have different representation depending on the basis we use. And to pass from one basis to the other, the fundamental quantity is it's provided by this quantity here that are basically the change of basis matrix element. That is, we recall from yesterday, in the case of Q equal to 0 and G equal to 0, these are the dipole matrix elements. But in general, these allow to pass also finite Q and finite G from the connection basis to the plane wave basis set. And depending on the quantity we are concerned with, there is a representation that is more practical. And if we consider, for example, the bare Coulomb potential, in the plane wave basis set, it is very simple. It is just one index object, just depends on, well, if you want two index objects, it depends on Q and G, whereas in the connection basis, it depends on 4 indices. So on the K point, K prime point that are coupled together and are whose difference is exactly equal to Q. So where Q being the transfer momentum in the interaction. And also the screen current potential has a much more complicated representation in the connection basis. Whereas on the other end, the self-energy and the propagator have a much simpler representation in the connection basis, and this is particularly so when we fall within the G0 W0 representation, since we basically approximate the self-energy to be diagonal. And so both of these quantities are one index object in the connection basis. And that's the reason for which in the Yambo, for what concerns the quantity related to the screening, these are computed in the plane wave basis set, whereas for what concerns the propagator and the self-energy, these are calculated in the connection basis. And the passage from one basis to the other, as I said, is provided by the oscillator strengths. And due to the fact that we have these two bases, in general, the connection basis and the plane waves basis set are strictly interconnected. And the extension of the plane basis set is regulated in Yambo by means of the cutoff energy C cut. So it's basically the cutoff of the plane wave energies. And the connection basis, the cutoff is provided by the number of bands that is included, that are read from the DFT calculation. And in general, both these parameters have to be converged. So let's now pass to look at the first ingredient, that is the reducible polarizability. It is calculated as the bubble diagram, I0 equals to minus E G0 times G0. And G0 is the propagator built from the connection energies, and it features both excitation energies and the excitation energies. So basically, we are jumping, we are either jumping from an occupied to an occupied state, or vice versa. And as this quantity, as the propagator is defined in the connection basis, here appears the change of basis matrix element that allow you to write chi in the space of the plane wave basis set. And we see that we have to sum on the valence and the conduction bands. So it is clear that the convergence parameter is in particular, so is the number of conduction bands, since okay, the number of valence band is obviously fixed, since you have to consider all of them. Another convergence parameter is the number of G vectors, that is basically giving you the size of your chi matrix, and also the number of K points, since we have calculated chi 0 for all the allowed transfer wave vector, and we have to integrate basically on the K grid. And obviously the extension of the K grid and the number of Q vectors we have to consider is the same. And that's the reason for which it is a very computational demanding part of the calculation. And the scaling, while in general is can very fast become very large due to the fact that we have to consider G prime, we have to consider all the conduction bands, and then we have a factor that is proportional to the K grid to the square, and also in general we can sample multiple frequencies, so this is generally proportional to the number of frequencies. Once determined the irreducible polarizability, we can then pass to calculate the reducible polarizability by solving the Dyson equation. And even here, we see that there is an implicit sum on G second to the fact that we have to solve the Dyson equation. And from the reducible polarizability, the inverse dielectric function is determined that as I explained yesterday, is directly related to the screened interaction, being it just epsilon to the -1 times the Coulomb potential. So, as I said before, in general, we want to limit the number of frequencies where to compute the screen Coulomb potential, due to the fact that this is at least a parameter we are able to control and we are able to manage. And if we are able to do the calculation of the screen Coulomb potential for a smaller number of frequencies, it is obviously very convenient. And to understand how it's possible to reduce the number of frequencies where we computed the screen Coulomb potential, it is useful to consider the relation between W and the irreducible polarization chi. In particular, from what we considered before, the reducible polarizability chi features Paul in correspondence of the transition energies. The transition energies, the energies that connect you from a state from the valence band to the conduction band, or vice versa. So in general, chi0 will feature a lot of poles in correspondence of these of the different allowed transition. And you can expect that in general, if you are considering a lot of conduction band, you will have a lot of poles in your chi0, and ultimately also a lot of poles in the screen Coulomb potential. And the idea from which you can try to simplify the screen Coulomb potential is to describe the screen Coulomb potential by means of collective transition rather of single particle transition. So the idea is that you can kind of represent together a lot of single particle transition by means of collective transition. And so in W, you will not include all the poles, but you will only include the most relevant poles that allow you still to be able to capture the most essential features of the screen Coulomb potential. And the first approximation that has been very successful and is actually still used a lot when performing GW calculation is the so-called plasmon pole approximation. And this builds on the idea that the most important collective excitation that to which you can describe screening is the plasmon pole. And indeed, if we look, for example, at the case of silicon, you expect that it will have a very strong response when you do a Hills experiment, but also an Hills calculation in correspondence of the plasmon energy. And so basically, what we will want to do is to describe the screening by means of this plasmon pole. And when you do an experiment and when you do a calculation, you find that the plasmon pole in correspondence, you will find this plasmon pole response for the macroscopic component of the dielectric matrix, but the plasmon pole approximation is applied to all the dielectric matrices, so also to the microscopic components and not only to the macroscopic component. But this idea works fine and has been implemented successfully. And within the Yambo Code, is the variant of the plasmon pole approximation that is used is as follows the postulation by Colby and Dietz. And the idea is that you can determine the plasmon energy omega and its associated residues by calculating the response chi at two different frequencies, at the static frequency and at the finite imaginary frequency, E omega p, and by default, this is set at one imaginary artery one artery along the imaginary axis. And by calculating the frequencies, by calculating chi at these two frequencies, you are then able to determine your plasmon energy and its associated residues, through which you can model your screen Coulomb potential. So your inverse derivative function, and so the screen Coulomb potential. And most importantly, this allows you to recover an analytic form of the screen Coulomb potential that applies for all the frequencies and for all the electric matrix, so for all the G and G prime vectors you are including in your calculation. This is obviously a very strong approximation. There are other methods to calculate the frequency response in Yambo. An extension of the plasma polar approximation that has been recently implemented is the so-called multipolar approximation. And the idea is that instead of describing the response by means of just one single plasma peak, you try to describe more collective excitation, but still a finite number, in the order of between 6, 10 number of poles. This is the typical idea, but you can even do more. And so you will have a series of collective excitation. And in this figure here, this corresponds to the red line. And if we compare to the blue line, you see that plasma pole, you just have one very large excitation. That is, so it corresponds ideally to the plasma peak. But the multipolar approximation is able to capture more features. And even more features are captured by the real axis integration, in so which you basically calculate the response for all for many frequencies along the real axis. So you basically do a direct calculation. But this is a very large calculation, and this is typically requires a number of frequencies that is in the order of hundreds of frequencies. Whereas in the case of the plasma polar approximation, you just have to calculate 2 frequencies. So in general, the idea is that if you're able to reduce the computational cost in frequency, it is very good. And in general, it also depends on what are your aims. Because, for example, the plasma polar approximation for semiconductors has been used a lot in literature and has been led to very good results. So we can now having this idea of how we can recover the screen Coulomb potential and have a good representation in frequency of the screen Coulomb potential, we can pass now to calculate the self-energy. And the self-energy is the GW self-energy. And the GW self-energy, to determine it, we have to perform a double convolution in frequency and in momentum space. And G0, okay, is again the single particle propagator, and W here has been written again in the Koneshan basis. And to pass from, as before, to pass from the Koneshan basis to the plane wave basis set, we have to introduce the change of basis matrix element. Since sigma, we want to calculate sigma in the Koneshan basis. Since we want to perform a perturbation theory and correct the different energies by including the correct correction that is provided by the self-energy. And if we plug in the W within this expression here, one can recover the expression we actually compute. In Yambo, the calculation of the self-energy is typically split into 2 parts, and in particular, one can calculate the exchange part of the self-energy and the correlation part of the self-energy, and this is convenient due to the fact that the exchange part of the self-energy just depends on the Coulomb potential V that does not have any frequency dependence. The frequency dependence is all retained in the correlation part of the self-energy. And so this expression here, the exchange part, is much more simpler to evaluate. In particular, it just depends on the Coulomb potential and its features rho to the square, and it just depends on the valence band index, whereas it does not depend on the conduction band. And this actually originates very simply due to the fact that the Coulomb potential does not have any frequency dependence. We just have to integrate the single particle propagator. But if we perform a contour integration, This leads basically to a summation just on the valence bands. And so this expression here you should be very familiar with, and is a very simple, well, kind of straightforward to evaluate, since it features just a single summation on the G vector and a summation on the valence band. Instead, the conduction band features a summation on, correlation part of self-energy features a summation on all the considered bands. And we can perform this integration. Sorry, here there is okay, no, this is fine. And obviously we can obtain the expression of this energy thanks to the fact that we are able to recover an analytic expression of the screen Coulomb potential. That is, okay, in this case, provided by for example, in the plasma pole approximation. So if we look at the dependence on the convergence parameter, you see that, again, we have a dependence on the plane wave cutoff that is single in the case of the exchange self-energy, and instead is double, the part of the correlation part of self-energy. We have a dependence on the number of conduction band, just in the correlation part of the self-energy. And I think that maybe it's important for you to know is the fact that in Yambo, in general, you can control the extension of the number of included conduction bands in the correlation part of the self-energy, differently from the number of included conduction band in the polarizability. And this is practical because in general, these two quantities can converge differently. And obviously, there is a dependence on the K-grid used. And so this, and if we perform the calculation, we are finally able to calculate the self-energy. Now, up to now, I've discussed a lot, like if we want the dependence on the frequency, the dependence on the number of conduction band, the dependence on the cutoff. The dependence on the K-grid is kind of hard to be controlled, since this requires a very different, requires to start with a different DFT calculation and to do different GW calculation for all the different K-grids. And in general, the convergence on the K-grids can be very slow due to the fact that ultimately the slow convergence originates from the Coulomb potential, in particular to have from the bare Coulomb potential that converges very slowly since it is a long-range interaction. There are, however, techniques to accelerate the convergence of the long-range interaction, and a common technique that is used in Yambo is a Monte Carlo integration of the bare Coulomb potential. And this, okay, I report here the convergence of the bare Coulomb potential, and you see that with the number of K points converges kind of slowly. When we pass to two-dimensional systems, the convergence of the bare Coulomb potential is even more problematic due to the fact that to properly treat two-dimensional systems, you don't use the standard form of the Coulomb potential, but use a truncated form of the Coulomb potential, since you want to avoid any interaction between replicas of your system, which otherwise will interact with each other due to this form of the Coulomb potential. And for the reason that this random integration method, this Monte Carlo integration method, are even more necessary when dealing with a two-dimensional system, which otherwise leads to this very slow interaction in particle. And when it comes, so as I was saying, in Yambo, there are methods to improve the treatment of the Coulomb potential. This is the V-average method. It is to improve the treatment of the bare Coulomb potential. And the idea is that you regularize the long-range limit, and this is typically applied on the wall of the wall of the self-energy, so both on the exchange and the correlation part. And you basically have to perform this integration within the different cells through which you subdivide your through which you have subdivided your system. So basically, when you perform the simulation, you describe your brilliant zone by means of a Monco's path grid. So basically, you can identify around each point if you want a mini Brillouin zone, and you perform an integration within the mini Brillouin zone, which you describe your system. And it has been seen recently that this V-average method may be not enough when it comes to lower dimensional systems, due to the fact that in certain cases for lower dimensional systems, also the dielectric matrix epsilon has a kind of a very sharp dependence on the Q vector, so on the transfer momentum Q. In this case, for the correlation part of the self-energy, it is suggested to perform a double average method technique on top of the average method technique. So the idea is basically, if you want that, the average method will regularize the Bernoulli potential. In the double average method, we also regularized the screen Coulomb potential. And so we treat the Bernoulli potential and the screen and the inverse dielectric matrix on the same base. And this allows to reduce the requirements on the K grid. So with all these ideas in mind, we can say that we are finally able to correctly assess the self-energy sigma, but we are not fully done yet, since we are still done. We still have a self-consistent problem to solve, since the self-energy depends on the quasi-particle energy we have to determine. So these two are interconnected, and this is a self-consistent problem. So what is typically done to calculate the self-energy and to determine the quasi-particle energies is to approximate the self-energy to be linear in the region of interest. So the idea is that the region close to the Konecham energies, in particular the real part of the self-energy, can be approximated to be to do not have a very strong variation, and so we can apply Newton's method. And so the quasi-particle energies can be determined from the Konecham energies by calculating the self-energy at the Konecham energy and then multiplying by this zeta factor that is basically, if you want, the linearization coefficient that is provided by the derivative of the real part of the self-energy with respect to frequency. And to determine this self-energy here, it is this zeta factor, and so the derivative of the self-energy, we calculate the self-energy for two different frequencies, and then we determine the derivative by finite differences. And in particular, the finite differences are taken exactly the Konecham energies and the Konecham energies plus a small frequency value that is equal to 0.1 eV by standard, but you can obviously control it. And by means of this linearization approximation, then we are able to calculate the quasi-particle energies. So I can summarize all the ingredients of the G0W0 method. So you start from a DFT calculation, for which you calculate so the Konecham energies and the Konecham wave function. From this, you can calculate the single particle propagator in the Konecham basis. From the single particle propagator in the Konecham basis, then you are able to calculate the irreducible polarizability Chi0, and we pass to the plane wave basis. Then in the plane wave basis, we calculate the reducible polarizability by solving the Dyson equation, and then the screen Coulomb potential. Once determined the screen Coulomb potential, we are able to calculate the self-energy. So in particular, here the correlation part of the self-energy, since the exchange part of the self-energy just depends on the Bernoulli potential. And once determined the self-energy, we are ultimately able to calculate the quasi-particle energies. And this is typically done in this linearization by linearizing the self-energy, so by approximating the behavior of the self-energy. So these are the main approximations that are typically used on performance calculation. So as I remind you, we fall within the GW approximation, so the screening is treated as RPA level. Then we approximate, like we suppose that the orbitals, Cornish-Hamm orbitals, are very similar to the quasiparticle orbitals, and the idea is that we do not perform a self-consistent solution, but we just perform one loop of the GW approximation, and we directly evaluate the self energy as being diagonal on the Cornish-Hamm basis. From what concerns the frequency treatment, we use the plasmon pole approximation. This basically, you represent the frequency by means just of this response, the most important responsive frequency space, and then we determine the quasi-particle energies through the linearization, through Newton's solution. So this was like an overview of the most important approximation that you will deal with, and also you will see in the tutorials later on, and which calculations are typically done in GW codes. Do we have any questions?
Thanks, Giacomo. And I can take the floor, I suppose.
Yes, please, Nicole.
Okay. Good morning, everyone, and thanks for being here. Let me briefly introduce myself again. My name is Nicola Spallanzani, and I work as a research technology at the Institute of Nanoscience of the National Research Council in Italy. I'm one of the developers of Yambo, and within the MaxIOE, I mainly work on the interface between developers, technology partners, and the management, helping coordinate activities and align developers' development efforts. So yesterday, Daniele already gave you an introduction to the Max Center of Excellence. Still, I like to briefly recall the main objective because it's important for the context of this talk. The goal of Max is to develop 5 lighthouse codes, including Yambo, so that they are fully ready to run efficiently on modern supercomputing architectures, especially in the exascale era. Now, exascale is no longer something in the future. The first exascale machine frontier has been operational for a while, and very recently, Jupiter, the first European exascale system, has also entered production. One key aspect to keep in mind is that essentially all modern supercomputers, both pre-exascale and exascale, are GPU accelerated. The only major exception so far is the Japanese Fugaku supercomputer. But even in that case, its successor is expected to include accelerators. So this is the direction the entire HPC ecosystem is taking. So with Max, our work on Yambo has focused on 2 main directions. On one side, improving parallel efficiency. On the other, porting the code to heterogeneous GPU accelerated architectures. At this point, Yambo is able to run on system equipped with NVIDIA and AMD GPUs, and we have also performed tests on Intel GPU nodes. In terms of programming models, we use CUDA Fortran and OpenACC for NVIDIA GPUs, and OpenMP offloading for AMD and Intel devices. So thanks to this, Yambo performs very well on systems like Leonardo, that is based on NVIDIA A100 GPUs, and Lumi, based on AMD MI250X GPUs. We see good performance and also very solid parallel scalability. More recently, I've also started testing Yambo on Jupiter, the new European exascale system. It's still early, but I can already say that the results look very promising. We will soon publish detailed scalability benchmarks on our public repository, but the link is in the next slide. So another important point is portability. Yambo can also run on ARM-based architectures, such as Fugaku supercomputer, where we have tested it up to about 1,000 nodes with very good parallel efficiency. At the bottom of this slide, as I said before, you can find the link to the repository where we collect the scalability tests for all the Max codes, including Yambo, of course, across several Euro HPC systems, and also other platforms like Fugaku, for example. Now, let me back for a moment and make a more general point. Electronic structure methods are among the most demanding application in high-performance computing. And this becomes even more true when we move to many-body perturbation theory. So we are really dealing with highly compute-intensive problems. This means two things. We need access to large computational resources, but we also need to use them as efficiently as possible. This is where the parallelization strategy of Yambo becomes crucial. In Yambo, every run level is parallelized using an hybrid MPI and OpenMP approach, and this is tightly integrated with GPU offloading. The key idea is that we distribute the workload across multiple levels of parallelism. Depending on the calculation, we can distribute over K points, Q points, bands, quasi-particle states, and other degrees of freedom. So let me give you a concrete example. Here we are looking at the run level used to compute the linear response matrix. Conceptually, the response matrix chi is obtained from the independent particle response function chi naught. In this case, we can explore up to 5 MPI parallel levels plus OpenMP. The first level is over Q points, the transferred momenta. This is what we call an embarrassing parallel level because each Q point is completely independent. So there is essentially no communication. I hope that in this slide you can follow the structure of the parallel used thanks to the color scheme that you can see in the slide. So other levels, bands, K points, and G vector are more interconnected. However, they are still based on sums or integrals, so communication between processes is relatively limited. Typically, the main communication happens at the end of the loops through MPI reductions. Now, Yambo can automatically choose how to distribute processes across these levels. But in practice, this is not always the optimal solution. So we strongly recommend that user manually tune the parallelization using input parameters, like the one that we can see at the bottom of this slide. Here you can see an example configuration for this run level. We are using 64 MPI tasks with 4 threads each. And the production of the parallelization that are the parallelization factor that are the number that you can see in this line. So the product of this number must match the number of MPI tasks. Each level has its own pros and cons, of course. For example, band parallelism is very good for reducing memory per process. So it's always a very good solution, a very good choice. K-point parallelism is efficient, but may duplicate some data. Q-point parallelism is ideal because we have said that is embarrassingly parallel, this level, but can sometimes lead to load imbalance. So there is always a trade-off, and understanding it can make a big difference in performance. So instead of keeping this discussion purely theoretical, let me show you some actual numbers. So the benchmark I'm using for this in this case is a full GW workload for a graphene cobalt interface. The first thing that I want to highlight is the importance of balancing MPI and OpenMP parallelism. I ran a series of tests on 2 CPU nodes of the Carolina cluster. Thanks for providing us the resources to these clusters. So each node has 128 cores, and we can distribute them in different ways between MPI tasks and OpenMP threads. If we start with a very few MPI tasks, the first line of this table, and many threads, for example, 2 MPI tasks for node and 64 threads each, the performance is quite poor. As we increase the number of MPI tasks and reduce the number of threads, as you can see also in the plot, performance improves significantly. The best solutions, the best results, sorry, are obtained around 8 MPI tasks per node, which is 16 threads per task, or the symmetric configuration. The difference between these two configuration is very small, so I decided to analyze both in more detail. So let's start with the case of 8 MPI tasks per node. Here I show how the performance are distributed across the different parallel levels. Since this is a relatively small test system, I begin with assigning all the process to the conduction bands, which are quite numerous. You can see the number of the at the bottom of this slide. So already this gives a very good performance. If I start moving process to valence bands in the second line, which are much fewer, the performance actually gets worse. The same happens when using most of the other levels. The only exception is the Q-point level, where we see a small improvement. Now, if we move to the 16 MPI tasks per node case, we have more flexibility. In this case, we can distribute processes across multiple levels more efficiently. So this is why I started with the case where I'm distributing 2 processes in every level. Starting with this balanced distribution already gives decent efficiency. But by tuning the distributions, for example, assigning process only to Q, G, and conduction bands, we can significantly improve performance. So the key takeaway here is that having multiple parallel levels gives flexibility, especially at a large scale. Of course, this is a very small example, so it's not exhaustive. But for very large systems, this can become essential. So now to better understand why, even for something like Q-point parallelization, which is embarrassingly parallel, we eventually stop saying improvements, let's take a closer look at how MPI parallel levels are actually managed. Let's imagine we are running with 8 MPI tasks. When I say that I assign, for example, 2 processes to a given level, what I really means is that I am dividing the MPI task into 2 groups. If then I assign 2 processes to another level, I am further subdividing those groups into subgroups. And if I add a 3rd level, I end up creating subgroups and so on. So in practice, the difference, the different sort of parallel levels correspond to a hierarchical partitioning of the MPI task. Here, another important thing to understand is that every process communicates with the other process of the same group and a subgroup, and only the leaders of every group communicate with the other leaders. So this reduces a lot the communications between all the MPI tasks. So now let's go back to the case of Q points parallelization. If I assign 2 processes to the Q level, I create 2 groups. In this example, the one group will handle 4 Q points and the other will handle 3 Q points. Sorry. So there is some imbalance, but it is still relatively small, and overall we will gain in performance. However, if I increase the parallelization and assign 4 processes to the Q level, I now create 4 groups. In this case, the first 3 groups handle 2 Q points each, while the last group handles only 1 Q points. Now the relative imbalance becomes much larger. The relative imbalance, of course. As a result, some processes finish earlier and remain idle, while others are still working. This leads to a load imbalance across processes and ultimately to a loss of performance. So now let's now move to GPU porting. The first implementation was based on CUDA Fortran, and later extended to OpenACC and OpenMP. To keep the code, Yambo Code, maintainable, we avoid duplication by using preprocessor macros to select the programming model at compile time. We also rely on wrappers, on a wrapper library named device_xlib, and on GPU-aware external libraries for linear algebra and fast Fourier transformation. This allows us to increase MPI, OpenMP, this allows us to integrate MPI, OpenMP, and GPU offloading in a clean, efficient way. As you are seen earlier, at the beginning of this presentation, this approach scales very well on modern architectures. So what is device_xlib? It's a Fortran library that we developed to simplify GPU programming. It provides wrappers for device-related operations such as memory allocation and data transfers. It also interfaces with optimized the library like QBLAS, MKL, and RockBLAS. And it supports multiple programming models, CUDA Fortran, of course, OpenACC, and OpenMP. So it essentially gives us a unified layer to write portable GPU code. From the user perspective, device_xlib provides a Fortran module which are routines grouped by functionality. So you have routines for memory management, data movement between host and device, and linear algebra operations. This helps keep the code clean and easy to maintain. So I actually have a few more slides that go deeper into device xlib and GPU porting of the Yambo code, but they are quite technical and more suitable for developers. So I will stop here my presentation, and thank you very much for your attention.
So I'm Fulvio Pagliari. I also work, like many of the Yambo developers, at the Nanoscience Institute in Modena. And today we're going to discuss about excitons. And the main quantity, the main observable that I will use for this discussion is optical absorption. Although we will see later that this applies also to other spectroscopic observables. I don't know if you can see my mouse. In any case, on the right, you can see, okay, perfect. This is an absorption spectrum of a 2D material, and the yellow bar is the band gap. In many semiconductors, and even more into the systems, when you calculate absorption, we see some signal, for example, these discrete peaks. What? Non si muove il mouse. Okay, well, I will just point you to where you have to look. As I was saying, we can see signal below the energy of the quasiparticle band gap. Right? And this signal is explained in terms of electron-hole bound pairs. In other words, when we excite an electron, it remains correlated with the hole that it leaves behind, creating what we call an exciton. And this type of interaction between electrons is not described as at the DFT level. And that's the reason why we need to get one step above DFT into many-body perturbation theory. In particular, the object, let's say the formalism that we use to describe exciton relies on the so-called Bethe-Salpeter equation. But let's take kind of a step back. Okay, so the main quantity I will deal with is optical absorption. So we have on the top left, light enters a crystal. The electronic structure of the crystal gets polarized and then modifies the electromagnetic wave that then gets measured, transmitted or reflected, and this gives us the absorption spectrum, gives the part of the incoming light that gets absorbed, the energy that gets absorbed and inside the system. We have also, for example, the inverse, if you want, phenomenon. First, we create an electron-hole excitation, then we wait a little bit, then the excitation recombines, emitting a photon, and this is typically called luminescence. And the picture that we have, normally, we have the band structure of our material, and if the photon energy is at least the energy of the band gap, then an electron can absorb the photon energy and be promoted from valence to conduction. No, we will see this picture is more complicated, but what is important to know is that now we are looking at the so-called neutral excitations, because creating an electron-hole pair does not change the total charge of the system, unlike the case of photoemission that we have seen yesterday in the context of the GW approximation and so on. Okay, so now we are dealing with neutral excitations. Well, why we are so much interested in this? Obviously, doing theoretical spectroscopy gives us insight into the microscopic structure of the system. So it's basically its quantum and microscopic properties. And in particular, we do need. Oh, just. Okay. Nobody told me. Sorry. Yeah. Sorry. So they just told me that the slides are not moving. So let me share again. Okay, let's do the entire screen this time. Yeah, I was debating how to share this stuff. Okay. Now they move, and the mouse also moves. Okay, thanks. Okay, sorry, let me just briefly go back. So this was the second slide. about the optical absorption and luminescence. These are the processes, is what I said. So let's just go ahead. Why are we interested in theoretical spectroscopy? And in particular in excitons? Because for many systems of interest right now, well, we can say in most semiconductors, but most importantly in two-dimensional systems, excitonic effects dominate the optical response of the systems. So we need to go beyond DFT in order to understand and possibly engineer the properties of these materials. For example, here is a very famous figure of various possible monolayer 2D systems put together. No? If you want to describe the properties of this, so the optoelectronic properties, we really need to kind of have a nicer description of the electron-electron interaction than what is provided by DFT. And we are not obviously just interested in layered systems. There are many systems where excitonic effects are important. Imagine, for example, systems for energy production. Like this is a particularly weird perovskite crystal. And this, again, can be used to generate a photocurrent, right? So light enters, and then the electron-hole pair gets separated by a field, a gate voltage, and then we have current. And for these, we need, the optical excitation of the system to be the correct energy, to be intense enough, and so on. So this is stuff that we can study with first principle simulations. But what we need to study is basically many body effects in the neutral excitations. Okay. Now, let's start in the long road that will lead us to the Bethe-Salpeter equation. And I will start it with a recap of Claudia's talk from Monday. So if you remember, she talked about linear response theory in the context of the RPA approximation. And this is exactly what we are going to do, linear response. So here we have a macroscopic material. We have a plane wave here that is traveling toward the vacuum space and then enters in the system, our macroscopic isotropic homogeneous system, and gets attenuated. No? How do we describe this process of attenuation? Via the Maxwell's equations, of course, right? So in the vacuum, we have the propagation of the wave, and there are no sources for the electromagnetic field. It's just the wave propagating. In the material instead, since it gets polarized after the wave enters it, we have some induced density and induced currents that create induced fields that modify the external field, right? And this process is called polarization of the system in general, and is described by this tiny epsilon function, which is, very well, is the dielectric function. So, that this will be actually the main quantity that we would like to compute, right? Okay, so we can obviously solve these equations. And in the vacuum, we have the homogeneous wave equation. And of course, as the picture already spoilers, the solution is just a plane wave. So if we compute the intensity, here at the bottom is just constant intensity. That's not the case anymore inside the system, because inside the system we have the inhomogeneous wave equation, because we have all the induced fields, right? The polarization of the field. Now here we have the sigma quantity for convenience, is the conductivity, but all these optical functions are related. So the conductivity is related to the dielectric function and so on. We can solve the homogeneous wave equation, but the solution is not anymore a plane wave, of course. The solution is an attenuated wave that has here still an oscillating part like the plane wave. Just now the wave is traveling at a speed c divided by refractive index n, right? And the refractive index also is connected to the dielectric function. But then we have a real part of the solution, which is an exponentially decaying part. So if we now compute the intensity, it's not anymore constant, but it's exponentially decaying like in the figure. And we can lump all the decay part in this coefficient alpha, the absorption coefficient, that gives exactly the rate of attenuation of our wave. And again, this absorption coefficient can be computed once we know the dielectric function. Okay, in particular, the most important part, the imaginary part of the dielectric function. So this is what we can learn with a macroscopic point of view. However, the macroscopic Maxwell's equation, they do not give us any prescription about the formula to use to calculate epsilon 2. So we don't know the formula of epsilon 2. And this formula depends on the microscopic description of our crystal. So we have to enter into the microscopic field of view. And the key point that I would like to stress for all this presentation is that the formula that we use to calculate epsilon2 depends on the approximation that we use for the electron-electron interaction. So the interaction between electrons, we can describe it at different levels of approximation, and this determines the expression that we use to calculate the absorption, for example, in this example, okay? Now, let's try to make this a bit more clear, and we go inside the lens, and we go in the microscopic, let's say, scale. For example, here, the microscopic scale of a crystal. And of course, now we cannot say that the system is homogeneous. Obviously, it's a crystal, and the electron density is not uniform, but is actually modulated by the crystal. So now the epsilon acquires a non-local spatial dependence, as you have seen many times in these 3 days. Fortunately, we have still an advantage because the system is at least periodic in space. So we can define a reciprocal space for this. In this case, it's an hexagonal lattice, so the reciprocal space is a repetition of hexagonal unit cells. And we can express our dielectric function in a reciprocal space. The non-local spatial dependence, then we can lump into this tensor dependence on reciprocal lattice vectors. So it will be a function of a momentum that is always inside the repeated Brillouin zone, and then a tensor in the non-local part, which determines where we are in the full reciprocal space. Okay, and this you have seen also is basically this just a recap of what Claudia already said, right? Very good. Now we want to calculate it, no? So we need to find the formula, as I said before. And so you can, with arguments also from Maxwell's equation and Poisson theorem, you know that the inverse dielectric function is given by the main quantity that determines the inverse dielectric function is the variation of the electron density with respect to the external incoming field, right? And this variation is called the susceptibility. Okay, so you see that the problem of computing epsilon is in reality the problem of computing this functional derivative, right? Now I'm going to do a trick because I don't want to deal with the epsilon minus 1. So we'll deal with the epsilon. And to do this, I will slightly redefine the susceptibility. So the equation above is the textbook definition, okay? But actually, I can redefine a little bit and say that the susceptibility is the variation of the density with respect to the macroscopic field, which means the external field plus the induced macroscopic field internal to the system. This is not so important right now. It's just a trick so that I can talk about epsilon and not epsilon minus 1, okay? And I call this variation the response function chi, or to be more precise, chi bar, because defined in this way, it's the short-range response function, not the full one, but it doesn't matter. The Coulomb potential in reciprocal space is this one, and so now we have this expression. Again, we don't know anything because all the complexity now is in this chi. So we can say we didn't gain much. But actually, we did, because now you know that the electron wave functions can be expressed in a basis of G vectors, in a basis of plane waves, but they can also be expressed in a basis of block states, right? You diagonalize the Kohn-Sham Hamiltonian, and then you have the wave function in the basis of crystal momentum and the band index. So in order to make the connection between absorption and electron hole pair generation, it is very useful to also change the basis of this to the block basis. Okay, so now this is what we are going to do in the next slide. It's just a change of basis. Nothing particularly crazy. So you see here, we have now expressed our chi in the basis of transitions. And of course, here we have the basis change coefficients, right? So these are just coefficients that pass from one basis to the other. But now the chi expressed in this way really makes it clear that what we are describing is the fact that we have a transition between valence and conduction at a certain momentum q of the external field. And this chi technically will couple this type of transitions, right? Obviously, we can do, since in this example for these slides, we are talking about optical absorption. We can do even another simplification. We get rid of the q, right? Why? This you know much better than me for sure. Because if we consider an external field for a typical bandgap, let's say optical, the wavelength of this field compared to the length scale of the unit cell is extremely larger. So from the point of view of the unit cell, the field is approximately constant. So this oscillating plane wave part, we can just expand to first order. And if we do this, you see that these elements simplify a lot. The Q comes out and basically simplifies the Coulomb interaction. And here we are left with these matrix elements that are the dipole matrix elements. They give us the strength of the electron-right coupling in this dipole approximation on the macroscopic limit. And this is something that one can compute at the DFT level. So finally, we have this expression, and it's pretty simple, it seems, right? But in reality, it's not so simple. Okay. Finally, now we can try to calculate it. And now we enter really in what I said before, that depending on your electron-electron interaction, the shape of this chi will be different, okay? So let's start by considering a simple non-interacting system. For example, we have the Kohn-Sham electronic Hamiltonian. So we have the Kohn-Sham band structure. And these, you know, are effectively non-interacting electrons, plus our external field. And then you can show that the chi in this approximation, which is the independent particles approximation that you have seen on Monday, also in the tutorial, is given by this expression. So this is really an electron hole, no? Conduction minus valence. And very obvious, I mean, this is famous for this, is diagonal in the transition basis. So in reality, we do not have this double sum because at the independent particle level, the transitions are not coupled because the electrons are not interacting, right? So since it is diagonal, if we take the imaginary part of this, it becomes a delta function. And then the final expression is this one, okay? And if you remember when you studied the time-dependent perturbation theory, this is really the Fermi golden rule for like first-order time-dependent perturbation theory. So this is basically we recovered a textbook result. I remind you why we are doing all of this. You remember, no? The absorption rate, which is given by epsilon. So this is the reason why we are doing all of this stuff. Okay, so at this point, these quantities, the dipole matrix element and the energies, we can compute with DFT. Or if we do a GW calculation, this can also be the GW energies, right? The quasi-particle energies. So we have the correct band gap at least. Okay, so this is the first step. But as I said at the beginning, this certainly does not describe the situation of two-dimensional systems, systems with low screening, and so on, where you have electron bound pairs. So what do we do? Well, we have to continue, we have to basically refine our description of the electron-electron interaction. In this Hamiltonian, we have 0 electron-electron interaction, although there is some implicitly embedded in the Kohn-Sham electrons. In reality, there is nothing here. And this is the figure from the tutorial that you did on Monday, you know, the independent particle absorption. Okay, so then you know from Claudia Stork that we can actually do something better, including the so-called local field effects in the RPA approximation. And this corresponds to including in our Hamiltonian the variation of the artery potential due to the induced density inside the material because of the field that is polarizing the material. So we are now modifying the interaction, but only the artery part, which is the classical part. And this gives us the RPA expression for the epsilon that you have seen on Monday. But actually, this is not really the most refined description that we can use for the electron-electron interaction, right? We have something more at our disposal, right? We have the GW self-energy. So it's much more than a Hartree. It's Hartree plus screened exchange. So why not using that? That's really the highest level that we can do. So we also add the variation of the GW self-energy with respect to the external field. And this, of course, as you know very well from Andrea's lecture and also Giacomo's explanation yesterday, depends on the gains, the full gains function of the system, let's say. We consider it a static self-energy, okay? So the interaction between electron and hole from this Hamiltonian is always instantaneous. But still, it is described at the GW level. So we have W, the screened non-local interaction included in our description of linear response, okay? And this is what leads us to the Bethe-Salpeter equation. In fact, by the way, of course, you know from yesterday, the RPA level of approximation is still used to compute the microscopic epsilon that goes into GW, right? So this is really kind of a ladder of approximations that we are doing at this point. Okay, so if you now express chi, the response function, for an Hamiltonian with this interaction, then you see it is much more complicated because we have the independent particle stuff that comes from this, no? But also then we have all these parts that come from the new interaction that we have added. So the Hartree part gives us this term, 2V, the 2 is a spin stuff, and then the GW part gives us this very important term, W, the screen interaction, which is a binding term. So it's what will produce the fact that the electron bound state will be at lower energy than the bandgap. You see here, I am expressing this in this form, like chi equal to the inversion of some quantities, because this is a Dyson-like equation in its inverted form. So it's similar to other Dyson equations that you may have seen for example, for the quasi-particle equation and so on, but for the response function. And this is what, in our context, we call the Bethe-Salpeter equation. The famous Bethe-Salpeter equation basically can be expressed with this formula. Okay, so now we have a problem because you see that this new chi that includes the Hartree screen exchange interaction is not diagonal anymore in the block basis. Why? Well, because the interaction is not diagonal, obviously, otherwise it would be non-interacting. So what we can do is another trick, even before solving it. Why don't we switch again to another basis in which all this expression is diagonal? Okay, so far, very simple. So now we have done an additional change of basis. Here are the coefficients to a new lambda basis, which is the basis of the excitons. And we chose the lambda basis, of course, in such a way that now the chi lambda will be diagonal. Okay. Now, these green quantities is basically, we can lump them in a kind of exciton dipole. And then this, we have to find its form. But we know its form because it's diagonal. So this is how we can simplify the expression. So we call the basis chain coefficient A. And here we have the dipoles. Since it is diagonal, it must have, the chi must have this shape, right? Like as a pole with a certain energy. But now this energy, E lambda, will not be the difference between conduction and valence, will be a different energy. Okay? And this is where the solution of the Bethe-Salpeter equation comes into play. The Bethe-Salpeter equation gives us the purple quantities here, the exciton energies and exciton coefficients. And the way that we do it is that we take the chi and we basically recast it as the mathematical resolvent of a model two-particle excitonic Hamiltonian. This is a matrix, and we diagonalize it. So we have basically reduced all the problem of absorption with electron interaction into the diagonalization of a specific Hamiltonian, whose eigenvalues are the energies of the excitons, and the eigenvectors are the exciton coefficient, or give us the wave function of the excitons in general. So basically what you do in the code is constructing this Hamiltonian and diagonalizing this Hamiltonian, right? In order to then calculate this expression. Before going to this last part, which is the numerical part, let me give you some examples. For example, here is the system from before, is monolayer boron nitride. And here is the absorption that I get if I compute it in the independent particle approximation. So the simplest non-interacting electron that I can calculate from the textbook with time-dependent perturbation theory. So we have excitations that start at the energy of the bandgap and then continue. And the dipole matrix elements are basically contain the electronic wave functions, which are periodic, you see, in the unit cell of the lattice. And this describes basically transition from valence to conduction. If we now go to the Bethe-Salpeter, everything is changed. We have huge peaks below the absorption, what we call the quasi-particle bandgap, where basically the oscillator intensity is completely sucked by these important peaks, and which look like discrete peaks. And again, this new dipole, the exciton dipole, now involves the wave function of the exciton, which is not anymore periodic, it's not anymore lattice periodic, but is the correlated wave function of electron and hole. And we can reproduce this by saying that these peaks, for example, this peak is given by a linear combination of several valence to conduction transitions, and these orange plots show the area in a reciprocal space where the A coefficients are non-zero. So it's not anymore a single transition, but it's a sum of transitions that is weighted basically by the Bethe-Salpeter equation. That means it's weighted by the electron-hole interaction. And in this particular case, it will be this area around K that gives rise to this peak. Okay? And the reason why these peaks are so prominent, in this case, we have a 2 electron volt binding energy between the quasi-particle band gap and this one that we call the optical gap. It's because we are dealing with a 2D system, right? So in the 2D system, there are two physical effects that increase the binding energies of exciton. One is the spatial confinement of electrons and hole in like a 2D slab that basically increases its kinetic energy. And the second and very important one, that is often said, is that we have basically zero or very much reduced electronic screening in a layer system because it's mostly vacuum, right? So it's not a bulk, and the electron and hole can really interact very strongly with not so much screening from the rest of the electronic density. Okay, perfect. So this figure to the left you have seen before. This shows, for example, how with the Bethe-Salpeter treatment we go beyond the RPA description and we have a very good description of the absorption spectrum of silicon. Going back to my example of two-dimensional systems, this is molybdenum disulfide. And again, the Bethe-Salpeter equation allows you to capture the onset of the optical absorption in this material, which is for these famous two peaks, the A and B exciton. Here we have to include spin-orbit coupling and Bethe-Salpeter in order to obtain agreement with the experiment. Now, this is just an example related to optical absorption, okay? I did not discuss other things that we can do, and you can do directly with Yambo. One thing is to solve the Bethe-Salpeter equation at finite momentum, so not just in the optical limit, but for excitons with a finite, finite center of mass momentum. And you see that different dimensionalities, you can find that the dispersion of the exciton energy has some peculiar behaviors, like in 2D can be linear, in 3D you can have longitudinal transverse splitting of exciton states. Not always you can approximate the exciton as like a parabolic band and so on. This has consequences if you want to do stuff like exciton transport, diffusion, you want to calculate group velocity, exciton thermalization, and so on. And this we can do, you can do, it's the state-of-the-art, let's say, implementation. And of course, since we can do this, we can also calculate yields. So I only discussed optical absorption. There is also electron energy loss spectroscopy, including at the Bethe-Salpeter level, or its a relative measurement, the inelastic X-ray scattering, that you remember are given by the inverse of the dielectric function. This is an example of a very famous paper on lithium fluoride. At each momentum, you have the yield spectrum like this. So these lines represent one single yield spectrum, and here you map in momentum the yield response of lithium fluoride. So this you can do, compile the code, this is a calculation that you can do. And there are also more things that you cannot do so easily. They are not considered state-of-the-art, but you can do with a little bit of effort that try to basically go beyond the limitations of the Bethe-Salpeter equation. For example, if we have an indirect system, so you have finite momentum exciton, you have like an indirect band gap, no? That are at low energy, then they will recombine, but assisted by a phonon. And will create a specific signal that you cannot describe with the regular Bethe-Salpeter equation. And so in order to describe this, you need to account for exciton coupling with the phonons. And here's an example on boron nitride. So this is something that, for example, we are working on a lot in Yambo. Another thing that you can describe, again, depends on exciton-phone interaction, is the broadening, okay, of the peaks in absorption. This is a temperature-dependent broadening. Then again, depends on the exciton scattering rate with other quasi-particles, but is dominated by the scattering rate mediated by the phonons. No? And here is an example where they track the experimental broadening with a Bethe-Salpeter calculation, including phonons. Another thing that you can do, and is very difficult in a Bethe-Salpeter context, is metallic systems, doped systems, okay? These are very difficult for numerical reasons because you have to describe very accurately the area in the Fermi surface, the area where the occupation changes. For example, in the screening, there is this transition, let's say, that from an electron at basically the same momentum from an occupied to unoccupied space, the so-called interband transition that is usually not described very well. And then also, in addition, the approximation that we do in the theory of the Bethe-Salpeter equation, for example, that the electron-electron interaction is instantaneous, becomes not valid anymore for metallic and doped systems. So it's a limitation of the Bethe-Salpeter, but now, you know, there is an active research in describing excitons in metals, and this can be, in principle, attempted. And this is an example in graphene, which is a semi-metal, and a description of the excitonic effects in the plasmon dispersion of graphene. So here you have the FT-RPA calculation of the plasmon spectrum of the yields, and here we have the Bethe-Salpeter, the inclusion of the Bethe-Salpeter, so inclusion of excitonic effects for a semi-metal, and here the exciton comparison. And then another thing, you know, that is even more out there is the charged excitation, is where you have electron, hole, and maybe another electron or another hole, because you have a semiconductor that is doped. So you have some charge, and then you have like these three particle stuff, the trions, and so on. All of this is beyond what we can compute by just compiling the code, but this is the object of active research. And the final, all of these relies on extending the Bethe-Salpeter equation to account the fact that excitons can kind of interact with other quasiparticles in the system. So it's the problem of exciton-exciton interaction. And in most of these cases, the solution is some attempt to extend the Bethe-Salpeter kernel with a dynamical component of the interaction. This is a bit technical. I just wanted to mention this. The exciton-phonon interaction is one such type of dynamical extension of the Bethe-Salpeter, which we recently implemented into Yambo, for example. And the final, but not for importance, application of the Bethe-Salpeter equation that is still active research is non-equilibrium dynamics. Here to the right, you see, for example, the generation, the time-resolved photon emission experiment, in which they generate signal below the band gap of this WSE2 monolayer. So they say, okay, we are generating an exciton in real time. And then they probe in real time that you have another excitonic signal pumping up at a different momentum. So this is all stuff that happens out of equilibrium, so beyond the realm of linear response that I have just explained today. And there are other things like the coherent oscillation, the thermalization of excitons, that you generate at high energy and then they kind of relax to the bottom of their dispersion and so on. All this on equilibrium world is a huge field that is now very important, and all requires kind of extending the theory and methods that we are using now, okay? Okay, so now let's go back for the last, I think, 5 minutes to what we do actually in practice. So how do we actually do in the code? What will you do in the tutorials? And as I said before, we have recast all the problems, all the theory that I hope you have optically absorbed, so to speak, from the slides before this one, into the diagonalization of these two particle Hamiltonian, the excitonic Hamiltonian, we can call it. And we have a diagonal part, again, which has the transition between conduction and valence, basically. And then we have the interacting kernel. As I said before, we have the part from Hartree, and then the part from basically GW. And this is the off-diagonal part. So it gives a shift in the diagonal part, but also it gives the off-diagonal part. And okay, so in order to solve this, the flow of the calculation is the following. Okay, first of all, you need the bands. So you do DFT, then you can shift the gap, or you do a full GW calculation. Okay. Then you calculate the screening. So we only need the static one. No, as I said, the Bethe-Salpeter state-of-the-art Bethe-Salpeter is static interaction. But if you use the frequency-dependent interaction for GW, you can still read that one. You don't need to recalculate a new screening just for that. Then the code builds the matrix elements. So it builds these two, basically. And finally, we have the diagonalization that gives access to the diagonal response function that I discussed before, which is then used to get the Bethe-Salpeter level of the dielectric function. Okay? And if we look at this Hamiltonian, we see that we can block separate it. We have the transitions, the positive energy transitions, so-called resonant, from valence to conduction, coupled to another positive transition. Then we have the negative energy transition, anti-resonant. And then we have the blocks that couple the resonant and anti-resonant transition. So in the end, we have this type of structure. And one important thing to mention is that this matrix is not Hermitian. Okay, it's pseudo-Hermitian, which means that the eigenvectors are not orthogonal, but the eigenvalues are still real. So it's a weird type of matrix, let's say. However, you should know that for most semiconductors, it is totally safe to neglect this coupling part because they basically give no effect, especially if the external energy is not close to zero, which for normal semiconductor, we expect it is not. And therefore, you just need to solve basically this block or these two blocks separately. And then these blocks, the blue blocks, are actually Hermitian. Okay, so in most cases, you will solve an Hermitian matrix, but which is much faster and the algorithms are much more efficient, right? But in some cases, you may need to go to the pseudo-Hermitian case. And let's just do some ballpark estimations here, how big this can become. Let's do some examples. No? The dimension of this matrix is given by the number of K points that you put in your system, the number of conduction bands, the number of valence bands that you put. So here you have to decide how many you want. No? Maybe you just want the top valence and bottom conduction, or maybe you need more. Okay, but this affects how big this matrix is. Then if you are including the coupling part or not, the precision at which you are doing the calculation, single or double. These two is because these are all complex numbers, of course, each matrix is a complex number. And then this gives you the total size, no? And in monolayer HBM, which is a very simple system with very few electrons, you basically have 5 electrons. And well, with 5 electrons, the resonant part is just 30 megabytes. You can also solve the full matrix with just 50, no problem at all. Monolayer MOS2 also is not so bad, 400 MeV. If we go to bulk MOS2, so double the number of electrons, monolayer MOS2 has a spin orbit, so it's double the number of electrons in general. Then the bulk is double the number of the monolayer, and so on. Okay, now already we are having some, we have to be careful that we can, host this matrix in our nodes and so on. And finally, if you go to like crazy systems, like crazy system, not from the point of view of DFT, of course, from the point of view of many body perturbation theory that can typically take like lower dimensions, lower number of electron system. If you go to this one, the matrix, even just the resonant one, with 300 gigabytes. So, okay, so this is something that you can estimate before you even run the calculation to kind of gauge, okay, how do I have to distribute my calculation? Can my nodes support loading so much stuff and so on? Okay. And by the way, yes, and in the tutorial, we just, of course, diagonalize the Hermitian one. Will be a simple example on monolayer MOS2. Okay, so how do we diagonalize it? And this is basically the final slide. Well, this is not so easy. So this is really more the technical point. We have different strategies and different libraries depending on, the type of machine that we are running on. For example, if we are running on a CPU machine and we just want to diagonalize the Hermitian part, we can do the full diagonalization with the normal Laplace, Scalapac libraries. But if this is too large, okay, which can happen, as I have shown you in the slide before, we can also have an iterative diagonalization that is called the Langchos-Haydock method that is implemented in Yambo. And this gives access only to the spectra, but is extremely faster than the full diagonalization. If we need access also to the energies and to the eigenvectors, so the external wave functions, not just to the absorption spectra, then we also have iterative solvers for eigenvalues and eigenvectors. In particular, there is this LabC library, which is working on CPU. And also there are new libraries that we are working on and to include, and they're also very fast. So this is really also another field of development, because as the machines change and also like the algorithms change, and so we are all involved in kind of doing this as efficient as possible. But we can also run on GPU. And on GPU, we have the same. So we have the version of the LAPACK for GPU in order to diagonalize, or we have both the iterative methods also on GPU, just for spectra, for eigenvalues and eigenvectors. The situation is more difficult for the pseudo-Hermitian case, as you can imagine, since the algorithms are less efficient or less used. For CPU, everything is fine anyway. You just have to use a larger matrix. For GPU, we are working on it, let's say, but you can still do the full diagonalization if you dare. And then we are developing in such a way that you can do on GPU also the Hermitian case. Okay, so with this overview, just to know that in the tutorial, you will use these three methods. So the tutorial will be about checking the performance of solving the Bethe-Salpeter equation with this full diagonalization, Lanczos-Haydock, and SLEP-C. And we will use the CPU for the CPU compilation for the tutorial. Okay, so let me just recap. So we discussed optical absorption, in general, neutral excitations. We know that in most semiconductors, for example, low-dimensional system, we cannot describe this properly with DFT, so because we need to describe excitons. And in order to do this, we have to the description of exciton depends on the details of the electron-electron interaction that we include. You need to use many-body theory to improve the approximations to the electron-electron interaction, okay? And numerically, we can recast all of this theory into diagonalizing an effective Hamiltonian. And all of these have to be implemented efficiently in softwares that can run on large-scale machines such as Carolina, where we are running right now. My approach to the theory was really like a bit simple for these slides. If you want to, really bring out the big guns, there are these two books. I mean, good luck. But I'm sure with a lot of persistence, they can be studied. These are really comprehensive. This is why I suggest them, but they are not easy, okay? And in particular, the approach using a response function to derive the Bethe-Salpeter is outlined also in this paper that I find is really interesting, but requires a little bit of previous knowledge, okay, of Edin equation, GW, this stuff. You have to have at least a little bit of knowledge before. Okay, with this, I thank you for your attention, and I think, yeah, I finished.
Okay, thank you for your talk. Are there any questions? Or maybe we can take questions later. And I didn't see anything in chat, so I would like to give the floor to our colleague from IT4I, Lubomir, and he will deliver to you a lecture about energy efficiency.
Okay, so as was said by Rutka, I'm Lubomir Jiha from IT4 Innovations. So IT4 Innovations is a supercomputing center in the Czech Republic. I'm gonna go directly to the topic. So for what we do for the MAX is the optimization of the hardware while running the MAX codes. So I'm gonna be showing a couple of results, of course, including a lot of results from Yambo. So starting from the beginning, essentially, if we measure energy, we need energy is this basic definition. It's power over time. So essentially, but to be able to measure the energy of the HPC systems, you need some monitoring systems, right? Some systems to measure the energy, and by pretty much by the quality of the measurement is pretty much defined by the sampling frequency. So if your code is changing the workload rapidly, that propagates to the power consumption, and to be able to capture those changes, you need to have a monitoring system that takes the measurements as fast as possible. So this is the example of an HPC application of the power timeline. And you see that as the application progresses in time, and it goes from the different regions which Each of those regions represents different workloads. The power consumption of the server that's running the code is changing, and we need to have some measurement system that are able to capture these quick changes so that we can adapt the hardware based on these. So this is an example of one of the power monitoring system that we have at IT for Innovations. It's on the Barbara system. It's called HDIM. This system was developed by Bull for their Sequana systems, and it is essentially an extra hardware, the FPGA, on the main board is taking the readings for the individual components. So it can give me the readings for the DIMMs. Those are the ones. Let me just the pointer. Those are the ones in the bottom. Then you can get independent readings for the processor. So there are two CPUs, so green, blue, and dark blue. And more importantly, what is not that common at such a high frequency, it gives me the power consumption of the entire node. So if I optimize, I doesn't want to improve only for the CPU, but I need to optimize for the entire node consumption. The problem is that if I add those two CPUs and the memory, there is still a part that is not covered. And that's the power consumption of all the other components of the main board, network card, PCI Express, controller, all this stuff that is it's additional that's not covered just by the consumption of the CPU potentially or the GPU. So that is also the case, if we take a look at like advanced HPC system like the one that is on the Lumi, which has a one CPU and four GPUs. So essentially, you have a fast in-band monitoring via RAPL for the CPUs. You have fast in-band monitoring for the GPUs via AMD ROCm. But what you're missing is the power consumption of the remaining components. So this is what we call the node power baseline. And this we cannot, on many systems that doesn't have the HDIMM, which is the majority of the system right now, even the Bull stopped shipping that power monitoring system because it was too expensive. So we need to somehow deal with the power baseline. So the power baseline in our case, it's usually calculated as some additional component that we do by the benchmarking on a given node. So if I have this Carolina GPU accelerated node, we have the IPMI monitoring to give us the entire node consumption, but that no monitoring is very slow. It gives us the readings every tenths of seconds, while the RAPL gives us the reading 1,000 times per second. So it is uncomparable difference, and we want to do quick changes, not such a slow one. So, but we can use the IPMI power consumption readings to measure the baseline. So essentially, what we can do, we can stress the GPUs. We have 8 GPUs, so we do stress all one by one, and then by subtracting whatever readings we have from the GPU, which is here, from the CPU, we get the power consumption of the components. Then we have the power consumption of the entire node. We add the IPMI reading, and then we get the baseline. This is what we want. And then you see that the baseline changes based on how many GPU is active. So this would be our power baseline that we can then put into this equation, and we can easily get the full node reading. And this is what we use on most of the system. And this is the node energy that we will be using in all the results presented in this presentation. So all these power measurements are done by our Merrick runtime system, which is a tool that allows us to monitor the energy consumption, but it also allows us to change some of the hardware knobs. So, for instance, mostly we will be talking about the CPU frequency, GPU frequency. Potentially, we can set
the power limit, and we can also control the number of active cores. So the Merrick runtime system is pretty much working in a sense that we instrument the code, we select the regions, we work, within the MAX, we work with the code developers to help us identify what are the most important regions. In many cases, this is already done because the codes already have a time measurements for the important region, so we can attach to these time measurements and start measuring the energy and potentially tune the hardware knobs. So Merrick essentially it is a tool, the runtime system that is linked with the code, and it can allows us to tune the hardware knobs on these parameters, and it allows us to measure the energy. So we're supporting different architectures, and this is pretty much a never-ending work. When there is a new hardware, we need to implement a support for that hardware, how to measure the energy and how to tune the frequencies or potentially other hardware parameters that impact the performance, and of course by that also impact the the power and energy consumption. So right now the latest hardware that is supported is NVIDIA Grace and the Grace Hopper. So the study that we did for the Max Code is mainly it's into phases. So the first phase that was finished, and it's the key results of this presentation is the static tuning. So by the static tuning, we mean that if I have a application, so essentially it's a runtime of the application. So for instance, a job submission. So if I submit a job, so I set the frequency for that entire runtime of the job. So this is a relatively easy change, and it is, but it is very strong because it is being implemented on several HPC system in a way that when submitting a certain job, you can select the frequency of that job. So this is practically usable for several sites. So okay, so if we do the static tuning, what do we measure? So usually we measure the runtime, we measure the energy consumptions, and we also can measure the number of flops that is being performed by the application. So we can measure the energy efficiency in the flops per watt. So we can measure the energy. Here the HDM represents the full node. So we report the energy consumption of the full node. We report the energy consumption of the individual components. RAPL, that would be the CPU. And we also then, when we do the static tuning, we set the limit how much we can extend the runtime, because usually when you change the frequency, you underclock the CPU, you are extending the runtime. For different workloads, this applies differently. But from the user and a system administrator point of view, you always want to have some limit. So we usually report like two cases: some when you do not extend the runtime, and the case where you extend the runtime as much as you can, and you really going for the maximum energy efficiency while running the code. That is applicable in some cases. For instance, if the cluster is not fully utilized, then you can have the luxury to extend the runtime, because then you're saving the energy. If the cluster is fully utilized and you don't want to extend and waste the compute time on the cluster, you simply select a limit how much you can extend the runtime, and then you have your potential savings in the energy. So this is the type of the report that we are doing. For Max, we evaluated the energy efficiency on these platforms. So it's AMD Zen 2, which is Rome, AMD Milan processor, the the Cascade Lake, Intel Cascade Lake CPU is the one that we have on the Barbara. And out of the later hardware, we have Intel Xeon Max, the Sapphire Rapids, which is equipped with the HBM memory. So we did the test for when the code is in the DDR and when the code is where the code uses the DDR and when the code uses the HBM memory for its data. We also did the tests for the NVIDIA GPUs. So essentially, the Zen 2, Zen 3, and A100 that represents a lot of the Euro HP systems that are currently operational. The petascale one and also the pre-exascale ones. For instance, Leonardo, Carolina using A100 GPU that's widely used. So these are the platforms. This is pretty much just the matrix that says where the individual codes were tested. So on these critical platforms, I was saying the Zen 2, Zen 3, A100 GPU, Sapphire Rapids, and Cascade Lake, all the codes has been tested on these. So this is example of the results that we then report for code. So this is example for the flare, and for every code, what we do is that we report three values, right? So we report the values for the default and the runtime and the energy consumption. Then we report results if we underclock, but we don't change the runtime. Here we extend the runtime by 1%, so we don't extend the runtime by more than 5%. And then how much energy we can save. And then the last line is that we don't care how much we extend the runtime. We're going for the maximum possible energy savings. So in this case, it was 9% on the ROM. And then the important thing is how much the runtime is extended. So we do this for all the platforms. You can see we don't report the flops per watt on NVIDIA A100 GPU because we right now don't have a support how to measure the flops on the NVIDIA GPUs. This is something that we're still investigating how we can do that. So where these results comes from? So the results comes from these tables where we actually do the sweep of the frequencies from the lowest to the highest. Where if I have a 0, that's the default settings, and then I start underclocking and measuring the runtime. So you can see what is the impact of the frequency on the runtime, the relative extension of the runtime, and then you see the measurements of the CPU and the energy consumption of the node. So you see that I have about 160 kilojoules on the CPU, but the entire node is about 200 kilojoules. So this is the reason, and we always optimize for this. And so then you have the compute node energy savings that, for instance, in this particular case, could be up to 19% when we mostly do not extend the runtime, could be 21% if we extend the runtime by 10%. But more important, more interesting is this particular configuration for Yambo. On the Intel CPU, we have two different knobs. So the search space and space that we need to optimize, it's a bit wider. So we have the core frequency, which is the frequency of the CPU cores, and that impacts the performance of the compute bound regions. Then we have the uncore frequency. The uncore region of the Intel processor is the one that contains the memory controller, last level cache, PCI Express controller, etc. So it's mostly related to the data movement in between the memory and the CPU. So for the memory bound workload, this is where you can control the performance. But more importantly, is the other way around, right? If you have a compute bound region, you can underclock the core frequency and you don't see the impact. If you have a memory bound region, you keep the uncore frequency high, you can underclock the core frequency because your your cores are waiting for the data from the memory anyway. So this is the way how you can save the energy. So you can see that if that this is for the siesta on the Sapphire Rapids with the DDR memory, we can see that if we start underclocking the CPU at certain point, let's say 1.6 gigahertz, we start seeing some impact. And the same, this is the uncore on the x-axis, the core. If we go down, we can also find that up to reducing from 3.5 to 2.1, we can essentially get only 3% runtime extension. And that really translates to the second heat map on the right, where you see that this is the region where I can have some energy savings. So right now, if we take a look, let's say that I want to extend my runtime up to 3%, what possible savings I can get? So I see that if I go towards this configuration, I can get to 10%. If I extend my runtime extension to 5%, I can get to 13% for this particular configuration, 1.6 Encore, 1.9 core, and then potentially I can do, if I allow longer runtime extension, I can get potentially better savings, but you see up to 20% is 3.2. It doesn't give us extra while we're reducing the runtime. So one of the most optimal settings would definitely be this one, where we're close to 13%, and the runtime is less than a 5%. Again, similar results for the GPU. So when on the GPU, what we can do, we can tune the streaming multiprocessor frequency, which is essentially equivalent to the core frequency on the processors. On some GPUs, you are able to tune the frequency of the memory, but those are only GPUs that have the GDDR memory, while most of the HPC grade GPUs, they do have HBM memory, and that one we cannot tune the frequency. So this is, for instance, also the case of A100 GPUs, and more or less all the GPUs that are used by the HPC centers are using the HBM memory. So again, by properly, by setting underclocking the GPU, you can find a point where without the runtime extension, we can save up to 7% of the energy. If we extend the runtime by 10%, we can get to 11%, 10.5% of the savings. So, and this, out of this table, we extract the key messages for the user of the application. So this is the summary. Essentially, again, just a brief summary for that. These are the selected platforms that are very widely used on the Euro HPC system. These are the potential savings. So, for instance, if we take a look at the Yambo, we see that on the Zen tree we can get a very good savings, up to 20% without really extending the runtime. For the GPU, with our tests, and we will be redoing those probably. Without the runtime extension, there is no saving. If we allow some runtime extension, there can be potentially savings, but that is not that interesting for the Yambo. But it is definitely the other codes. They can exploit some underclocking to save the energy. So the next step of our work is that is our current work is the dynamic tuning. So essentially, that the Merrick, what it allows, if you go from a region to region, Merrick can set the frequency for that particular region. So again, if I have a memory bound region, I will have a low core frequency, high uncore frequency, and vice versa. So the dynamicity of the application, again, that's mostly what we exploit is the arithmetic intensity of the different regions. So as application goes, it has a phases where it loads the data from the disk or save the data to the disk. Then it goes to the phases where it does a lot of the compute. Then you have some communication regions. They all exploit different workload, and that the different workload has a different sensitivity to the frequency. So for instance, if I'm waiting in the MPI barrier, my CPU doesn't have to run on the full frequency. It can be underclocked, and that can save us time. If I'm saving the data to the disk, I can underclock, and again, it will not impact my performance, but I will be saving the energy. So this is the methodology that we use, and essentially how it is done. That then you have a code. It has what we call a significant regions, and each significant region has a different optimal settings. And as we entering a region, the Merrick instrumentation is called, and that finds the optimal for that region and applies that. And if you go to the second region, that will happen again. So this is the methodology for the dynamic tuning. This is example of a Lattice-Boltzmann code that I just it's not related to the Max, but it essentially is a code that has a very strong compute bound region and very strong memory bound region. And you can see that if we take a look at the runtime for the compute bound region, and this is the encore frequency, you can see that we can underclock from 3 gigahertz all the way to 1.5 gigahertz. There is no impact on the runtime if we take a look at this line. And so the different lines are different, the core frequency, so it's compute bound. So you can see that if we underclock, then the runtime is extended. But if we take a look at the red line here, you can see that while we underclocking the encore, we're not having impact on the performance, but we are saving the energy. The memory bound region behaves differently, right? If I increase the encore, they do the runtime is shortened, so I definitely have impact on the performance. While if I for the energy, there is the sweet spot that I can change. So you see that the different regions have a different behavior for the tuning, and this is what we can exploit. So if I do if I have an application that has these two regions, and I do the static tuning, I need to find some common optimal point for both of the regions. That usually gives us some energy savings, but it also has an impact on the runtime. While if I do the dynamic tuning, I can get the most optimal for the independent workload, and that usually yields a lower runtime extension and provides better savings. So that's why we use the dynamic tuning. So coming back to the Yambo. So the Yambo actually, when we instrument these regions in the Yambo. So this first line is essentially the ones that we are important and that we use for the dynamic tuning. And we can also see that if we run the Yambo, this is execution on the Sapphire Rapids with the HBM memory. We can see that as we progress from the regions to regions, they do have a different power consumption. So there is a dynamic behavior in the application that can be exploited. We can also see that for this particular configuration, the XO procedure is the one that is taking most of the runtime. So that will probably, be the region that will dominate the static tuning settings. And then this is the second part of the timeline where I have also another HF and GW regions at the end of the simulation. So if I take a look at these, so now a couple of regions from the Yambo, I can see their behavior on this is AMD Milan. So the one that we have on the Carolina, the CPU. And you can see that we have, if we tune the core frequency, the regions behave differently. I mean, on average, we see that, of course, if we increase the CPU clock frequency, the runtime is getting shorter, but with a variation, right? The HF region, the runtime is getting is reduced marginally when I increase the frequency, while I see a big impact on the energy. And then I see then if I increase the frequency, I see some volley where I have the optimal energy consumption. For the RIM region, I can see that as I keep increasing the frequency, I keep getting better runtime. And for instance, for the XC potential driver region, I don't see that much difference in the energy consumption throughout the runtime. So this is for the Milan. If I take all these identical regions, their behavior on the different architecture right now, this is NVIDIA Grace CPU, is different. Of course, there is a common trend. If I increase the frequency, the runtime is getting better. But right now, all these regions which have a different behavior on the AMD CPU, they have more similar behavior on the NVIDIA Grace, and you can see that somewhere around 1.82 gigahertz, there is the sweet spot in terms of the energy efficiency, and all the regions have this sweet spot. And the shape of these curves is similar. So there is a same workload, different hardware. So that's why if we find the optimal for one hardware, it's not easily transferable to the different hardware. These are two quite different architecture. This is x86 CPU and this is ARM CPU. So that's the reason why we need to do this for the different architectures as well. So this is the result that I have for these main regions. And again, we can if we do allow runtime extension, this is what I have in this column, 10% up to 35%. So if you take a look at the 5%, this is the optimal settings that I have for the individual regions. And this is how much I can save with 5% runtime extension on the Grace. If I increase, then for 12, I can get more, 25%, etc. So this is for the dynamic. You can actually, in this particular case and in this particular tests, you can see that the static tuning is behaving very similarly. And of course, the reason is the XO procedure region, because if I take a look here, at the runtime in the default, I see that the XO procedure is the region that runs for 330 seconds, while the other second longest regions run for 10% of its runtime. So that's why even the static and the dynamic tuning is dominated by the XO procedure. But if we take a look at another test what they did, which is for the Sapphire Rapids with the HBM memory, we can see that I have two interesting regions here. And for the Sapphire Rapids, I can again tune the core and the uncore frequency. So I have this region called XO Redux. And for that region, I can see that independently of the set of the clock frequency of that are both core and the uncore, the runtime is about the same. So I can simply select the lowest core and the uncore frequency, and I will get up to 38% of energy savings without really impacting the performance. So the GW region, essentially that can run on the very low clock frequency, very low uncore frequency, and it needs a high core frequency. So I can get this runtime, 4% runtime extension, and again, I can save about 13% of the energy. So if this is just, I pick two regions that have some interesting workload, but again, if I do the summary of this dynamic and the dynamic tuning on the Sapphire Rapids with the HBM, again, I have a list of the regions. I have their best configuration. This is for the 5% runtime extension. And I can see which regions actually bring me the contribution. I see that about 45% of the energy saving comes from the XO Redux, 32% comes from the GW. The XO procedure, again, gives me a little bit lower savings. But in total, if we sum this all up, I mean, I have the chart below, which is essentially the one that is the most important. I can see that for this particular measurements, the difference between static and dynamic tuning is significant, right? For the 5% runtime extension, I can save 6% with the static, but I can save close to 12% with the dynamic tuning, and that's mainly due to these two regions. If I allow to increase of the runtime a bit more, you see that doesn't bring us any significant additional savings. So the most important configuration is this one, and this is the one that is shown in this table. Uh, what we are working on right now, it's the dynamic tuning for the GPU accelerators. So in the GPU accelerators, I mean, the thing that you try to do is to be as asynchronous as possible, right? I mean, so the GPU doesn't wait for so the CPU can do additional work for the GPU. So we don't use the notion of the regions of the GPU. The GPU runtime that we are developing right now is based pretty much on the performance counters. So we reading the performance counters on of the GPU accelerator with some frequency, and we calculate the arithmetical intensity of the given workload which is being executed. And based on the arithmetical intensity, we do select the GPU frequency. So it is fully transparent. The user doesn't have to annotate the code. We just reading the performance counters every 10, 100 milliseconds. This still depends on type of the GPU. And then we adapt the clock of the GPU based on these performance counters. I'm going to switch this. So the energy measurements, we also integrated with the UP4Max, which is the benchmarking platform. So on HP system where we can measure the energy, the UBET is not only measuring the runtime, but it can also measure the energy consumption, again, for the GPU, for the NVML, and potentially for the full node based on the baseline calculation if those are available. And that's it for me. Hopefully I'm in time because I didn't have a clock. If there are any question, please go ahead.
Hi, Lubomir. If I may, thanks for the talk. I think very, very interesting, especially these very fast results on Yambo. I had two questions. One is, so you've shown some this effectiveness of the dynamic tuning in Yambo. Is that somehow connected to the fact that we have barriers and imbalance such that then we can really save there?
So I don't know, for instance, what type of workload is in this region.
That is a barrier, but the Redux is a reduction operation and a barrier typically loading to some imbalance.
Yeah. So essentially that would explain, why you can simply underclock the code, the frequency as low as possible, and you're not impacting the runtime, right? So this probably, okay, if you're that would be the possible reason for this, actually, Andreas.
And then the second question is on GWPPA. So that is more surprising that you can really save that much. So I was wondering, is that related? So can we interpret that as due to, I don't know, some memory erase or is there anything phishing going on underneath?
So what is this tells me that the uncore frequency can be low and the core frequency needs to be high. So by just looking at the table, it tells that it is purely compute bound region that doesn't do a lot of memory communication. So it's mostly it is insensitive to the memory performance. That's what it says.
Okay, then it's good. So okay,
If
that is
then,
meant to be massive number crunch.
if I would be interested whether the code is optimal or not, it kind of tells me if I start underclocking the core frequency, if the code is fully optimal and can utilize the hardware units well, then this is what I would expect. That if I underclock, I see a significant impact on the runtime. if this would be a compute bound region, and I can underclock the core frequency, and I don't see a performance drop, then I would say there is a room for the optimization of that particular region. But if I see that there is a significant impact on the runtime, then the code actually uses the available resources well. And if I take the resources from the code, which means lowering the frequency, I can see that there is a significant impact on the runtime.
Okay, no, thanks a lot. Thanks a lot. Very interesting.